Between 1968 and 1972, 24 men flew to the moon, and 12 walked on it. The youngest of them is now 89 years old. The records they set during the Apollo program have stood for more than 50 years. Every spacecraft since has been measured against what they did with computers slower than a 1980s pocket calculator and a slide rule. Welcome to Space Cluster, where we trace the engineering the space age tried to forget, the rockets America buried, the reactors that worked, the programs that died in filing cabinets, in committee rooms, in budget cuts approved by men who had never seen a turbopump fire. We strip away the press releases to show you the technical reality of what humans built when they tried to leave Earth. In this 4-hour documentary, you will walk the entire Apollo arc, the missions they ran, the crews they trained, the 8 American astronauts who died before Apollo 11 ever flew, the spy mission hidden inside Apollo 8, the secret payload on Apollo-Soyuz, the classified record of Apollo 18, 19, and 20. Every chapter is grounded in NASA flight records, primary crew transcripts, and the engineering decisions that made the program possible.
July 20th, 1969. Neil Armstrong becomes the first human to walk on the moon. The triumph of American engineering. The victory of the space race. A moment when humanity looked up at another world and said, "We made it." But here's what they don't tell you in the documentaries. What gets edited out of the highlight reels. What NASA spent decades trying to bury. Before Armstrong stepped onto that lunar surface, at least 8 men died trying to get him there. Some were erased because their deaths were embarrassing. Killed by birds, by fog, by mistakes too mundane for the heroic narrative. Some were erased because their programs were classified, their missions too secret to mourn in public. And some were erased because admitting what killed them would have meant admitting NASA knew it was coming, that the agency saw the warning signs and flew anyway. This is the story of the Shadow Astronaut Corps, the men who paid for the moon landing with their lives and then vanished from history. Their names aren't in the textbooks. Their faces don't appear in the documentaries. But without their deaths, without the lessons written in their blood, we never would have made it to the moon at all. Walk into the Kennedy Space Center Visitor Complex today and you'll find a monument, the Space Mirror Memorial, a wall of polished black granite, names etched in stone, backlit so they seem to float in space. It's beautiful, it's solemn, and it's incomplete. The official story of the space race is clean. It's inspirational. It's Mercury 7 astronauts in silver suits, grinning at cameras. It's John Glenn orbiting Earth. It's Kennedy's speech about choosing to go to the moon not because it is easy, but because it is hard. The official story is about triumph, about American ingenuity conquering the impossible, about brave men riding pillars of fire into the heavens and coming home heroes. But there's another story, a shadow story, and it begins with a simple question. How many astronauts died before we reached the moon? Ask most people, and they'll remember Apollo 1. 3 men, Gus Grissom, Ed White, Roger Chaffee, killed in a fire on the launch pad in 1967. It's the tragedy everyone knows, the one NASA couldn't hide because it happened in front of hundreds of witnesses and made headlines around the world. But Apollo 1 wasn't the beginning. It wasn't even close. Between 1964 and 1968, at least 8 astronauts and test pilots died in the line of duty. Some in training accidents, some in classified military programs, some in ways that technically don't count as spaceflight fatalities because of arbitrary definitions about where the atmosphere ends and space begins. Theodore Freeman, Charles Bassett, Elliot See., Clifton Williams, Robert Lawrence, Michael Adams, and yes, Grissom, White, and Chaffee. 8 men, 8 families who got a folded flag and a closed casket. 8 names that should be as famous as Armstrong, Aldrin, and Collins, but aren't. Why? Because these deaths were inconvenient. Because acknowledging them would mean acknowledging that NASA was pushing too hard, moving too fast, ignoring warning signs in a desperate race against the Soviet Union. Because in the Cold War calculus of the 1960s, dead astronauts were bad for morale, bad for funding, bad for the narrative that America was destined to win. So they were erased. Not officially, not with malice, but through the quiet bureaucracy of institutional forgetting. Their accidents were ruled training incidents rather than spaceflight fatalities. Their programs were classified. Their deaths were mentioned briefly in the press and then buried under the next launch, the next milestone, the next triumph. The pattern was systematic. The erasure was deliberate. And it all started on Halloween 1964. Theodore Cordy Freeman was 34 years old, a husband, a father to a young daughter, and one of the brightest engineering minds in the astronaut corps. Selected in 1963 as part of the New 14, the third group of astronauts NASA recruited, Freeman was exactly the kind of man the space program needed. University of Michigan engineering degree, naval aviator, test pilot, the kind of guy who could fly anything and fix anything, who understood the physics of orbital mechanics as well as he understood how to coax a jet through a thunderstorm. He was supposed to fly to the moon. He almost certainly would have, given his skills and his position in the crew rotation. But on October 31st, 1964, Theodore Freeman became the first astronaut to die in the line of duty. He was flying a routine training mission that morning, piloting a T-38 Talon jet out of Ellington Air Force Base near Houston. The T-38 was NASA's workhorse, a sleek, supersonic trainer that astronauts use to maintain their flying proficiency and to travel between NASA facilities. Fast, nimble, reliable. Except when you hit a bird at 1,500 feet. A snow goose. A single bird in the wrong place at the wrong time, sucked into the left engine intake of Freeman's jet. The engine disintegrated. The aircraft lurched, hemorrhaging thrust and altitude. Freeman had seconds to make a decision. He could have ejected immediately, punched out, and let the jet crash wherever momentum and gravity took it. But there were neighborhoods below, houses full of families. So Freeman did what test pilots are trained to do. He stayed with the aircraft, wrestling it away from populated areas, giving himself just enough time to steer clear before pulling the ejection handle. He waited too long. When he finally ejected, the T-38 was only 200 feet above the ground, well below the minimum safe altitude for the ejection system to work properly. His parachute deployed, but there wasn't enough time for it to slow his descent. Theodore Freeman hit the ground at lethal speed and died on impact. NASA called it a tragic accident, an act of God, a freak encounter with wildlife that no amount of training or preparation could have prevented. And in a sense, they were right. You can't predict when a bird will cross your flight path. But here's what NASA didn't say. Freeman's death should have been a wake-up call about the risks of high-performance jet training. The T-38 program was pushing astronauts to fly constantly, to rack up flight hours in a jet that was unforgiving of mistakes, to operate at the edge of performance envelopes because that's what spaceflight would demand. Instead of reassessing those risks, NASA treated Freeman's death as an isolated incident. No significant safety modifications were implemented. The T-38 program continued unchanged, and the message was clear. Astronauts were expected to accept these risks as part of the job. If you died in training, well, that was the price of being on the team. Theodore Freeman's name was added to the Space Mirror Memorial, eventually. But his death was quickly overshadowed by the program's momentum, by the next mission, the next milestone. The first astronaut to die became the first astronaut to be forgotten. And the T-38 wasn't done killing. February 28, 1966. St. Louis, Missouri. Dense fog blankets, Lambert Field. the kind of weather that turns the world into a gray void where the ground and sky blur into a single, suffocating nothing. Visibility is near zero. Any sensible pilot would divert, land somewhere clear, wait for the weather to pass. But Elliot C. and Charles Bassett aren't just any pilots. They're astronauts, prime crew for Gemini 9, and they need to get to the McDonnell Aircraft Plant in St. Louis to inspect their spacecraft and run through simulator training. The mission is weeks away. The schedule is tight. They're behind, so they fly into the fog. C is in the left seat, the pilot in command. Bassett is his crewmate, his partner, the man he'll fly with into orbit. They're in a T-38, the same jet that killed Ted Freeman 16 months earlier. C begins an instrument approach, relying on his gauges and radio navigation, because he can't see anything outside the cockpit windows. Just gray, just fog, just the needles on his instruments telling him where the runway should be. He misjudges the altitude. Maybe the instruments are slightly off. Maybe he's a few degrees too steep on the approach angle. Maybe the fog is playing tricks with his depth perception. It doesn't matter. What matters is that the T-38 comes in too low, too fast, and slams into the roof of Building 101, the very building that houses the Gemini 9 spacecraft they've flown here to inspect. The jet disintegrates. Elliot C. and Charles Bassett are killed instantly. The debris from their aircraft damages the spacecraft they were supposed to fly. The irony is almost too cruel to process. They died crashing into their own mission. NASA's crew rotation system was rigid, almost mechanical in its logic. If a prime crew couldn't fly, the backup crew moved up. Simple, clean, no room for sentiment. So when C and Bassett died, their backup crew, Tom Stafford and Gene Cernan, became the new prime crew for Gemini 9. The men who had been waiting one level below Stafford and Cernan, Jim Lovell and Buzz Aldrin, moved into the backup positions. And that shift, that single rotation caused by a crash in a St. Louis fog, cascaded through the entire astronaut roster like falling dominoes. Crew assignments for future Gemini and Apollo missions shifted. The carefully orchestrated sequence of who flew when, who gained experience on which missions, who would be positioned for the first lunar landing attempts. All of it changed because two men flew into weather they shouldn't have. Here's the stunning part. If Elliot C. had pulled up 2 seconds earlier, if he'd cleared that rooftop by 10 feet instead of hitting it, Buzz Aldrin probably never walks on the moon. The second man to set foot on the lunar surface, one of the most famous astronauts in history, got there because of a training accident in bad weather. History turned on seconds. On fog, on a judgment call that went wrong. 2 more T-38 crashes, 2 more dead astronauts. And still, NASA hadn't learned its lesson. But there was something even more dangerous than a high-performance jet waiting in the program's future. Something that had already killed people in tests that NASA knew nothing about. A spacecraft filled with pure oxygen. To understand what happened on January 27, 1967, you need to understand combustion chemistry. In normal air, the stuff you're breathing right now, oxygen makes up about 21% of the atmosphere. Nitrogen and other gases make up the rest. This mixture is what we evolved to breathe, and it has a convenient side effect. It's relatively hard to start a fire, and fires that do start spread at manageable speeds. But pure oxygen is different. Wildly, terrifyingly different. NASA designed its early spacecraft to use 100% oxygen atmospheres at reduced pressure, about 5 pounds per square inch instead of the normal 14.7 at sea level. The reasoning was sound from an engineering perspective. Pure oxygen systems were simpler, lighter, and eliminated the need for heavy nitrogen tanks and complex gas mixing equipment. Every pound saved was a pound that could go toward fuel, instruments, or payload. But in pure oxygen, the rules of fire change completely. Materials that are merely flammable in normal air become explosively combustible. Things that won't even burn in regular atmosphere, metals, supposedly fire-resistant fabrics, plastics rated as non-flammable, can ignite and burn with terrifying speed in pure oxygen. The flame propagation rate increases by orders of magnitude. A spark that would smolder and die in normal air becomes an inferno in seconds. The military knew this. Between 1962 and 1965, the U.S. Air Force experienced multiple oxygen fire incidents in pressure chamber tests. Test subjects suffered severe burns. The risks of high oxygen environments were documented, studied, written up in reports that gathered dust in classified filing cabinets. But those reports never made it to NASA. Cold War compartmentalization meant that military test data stayed military. Civilian space program engineers, working just miles away from Air Force facilities, had no access to the lessons the military had learned in blood and burns. 3 agencies, 3 sets of fire victims, 0 communication. NASA was building a death trap, and the information existed to prevent it. But the information was classified, siloed, locked away behind security clearances and interagency bureaucracy. So, NASA engineers kept designing spacecraft with pure oxygen atmospheres, kept filling cabins with Velcro and nylon netting and foam padding, kept installing complex inward opening hatches that required minutes to unseal. And in 1967, 3 men paid the price for that institutional blindness. January 27, 1967, Launch Complex 34, Cape Kennedy. The Apollo-1 crew, Gus Grissom, Ed White, and Roger Chaffee, are strapped into their spacecraft for a plugs-out test, a full dress rehearsal of launch procedures. It's considered routine. The Saturn rocket beneath them isn't even fueled. This is just a systems check, a practice run to make sure everything works before the real launch. The test is plagued with problems from the start. Communication glitches, strange smells in the cabin, minor technical issues that pile up into frustration. Grissom, a veteran of Mercury and Gemini missions, is increasingly vocal about his concerns with the Apollo spacecraft. He's told colleagues that it has problems, that it's not ready, that he doesn't trust it. At 6:31 p.m., someone reports a fire in the cabin. In the pure oxygen atmosphere, pressurized to 16.7 pounds per square inch for the ground test, the fire spreads with a speed that defies comprehension, less than 15 seconds. That's all it takes for the entire cabin to be engulfed in flames. 15 seconds for the temperature inside to reach thousands of degrees. 15 seconds for the pressure to spike so high that the hull ruptures. The crew tries to open the hatch. It's an inward opening design, held shut by the pressure differential. The higher the pressure inside, the tighter it seals. Under normal conditions, it takes minutes to unseal the multiple latches and remove the hatch. Under fire conditions, with pressure spiking and smoke filling the cabin, it's impossible. Gus Grissom, Ed White, and Roger Chaffee die within minutes, killed by asphyxiation and thermal burns in a spacecraft sitting on the ground, not even fueled for flight. They die in a test that was supposed to be safe. They die because NASA used a pure oxygen atmosphere that turned their cabin into a bomb. Because the spacecraft was filled with flammable materials. Because the hatch couldn't be opened quickly. Because every design decision that killed them was a known risk that had been documented, studied, and filed away where the people building Apollo would never see it. The Apollo-1 fire forced NASA to stop, to redesign, to implement changes that should have been made years earlier. Outward opening hatches that could be unsealed in seconds. Nitrogen-oxygen mixed atmospheres that reduced flammability. Fire-resistant materials throughout the cabin. Improved wiring and systems to prevent ignition sources. These changes made Apollo safe. They made the moon landing possible, but they came too late for Grissom, White, and Chaffee. The Apollo-1 tragedy is the one everyone remembers because NASA couldn't hide it. It happened in front of hundreds of technicians and engineers. It made headlines around the world. It forced congressional hearings and investigations. The agency had no choice but to acknowledge it, to learn from it, to change. But there were other astronauts dying in programs so classified that NASA could pretend they never existed at all. June 30th, 1967. The U.S. Air Force announces the selection of astronauts for the Manned Orbiting Laboratory Program, MOL for short. It's a classified military space station project, essentially a spy satellite with astronauts on board, designed to conduct reconnaissance missions that automated systems couldn't handle. The program is so secret that most of the astronauts' work will never be publicly acknowledged. Among the selectees is Major Robert Henry Lawrence, Jr. He's 31 years old, a PhD in physical chemistry, an Air Force test pilot with impeccable credentials, and he's the first African American ever selected as an astronaut. This should have been a historic moment. This should have been front-page news, a milestone in the civil rights era, proof that the space program was finally opening its doors to the talent and courage of all Americans. But because MOL is classified, because the program's very existence is a military secret, Lawrence's selection receives minimal press coverage. No ticker-tape parade, no magazine covers, just a brief announcement and then silence. Robert Lawrence will train for a space station that will never fly. He will prepare for missions that will never launch. And 6 months after his selection, he will die in a training accident that most of America will never hear about. December 8th, 1967. Edwards Air Force Base, California. Lawrence is in the back seat of an F-104 starfighter, serving as an instructor pilot for a training flight. They're practicing steep descent approaches, extreme angle landings that simulate the approach profile a spacecraft would use returning from orbit. It's dangerous flying, pushing the F-104 to the edge of its performance envelope, diving toward the runway at angles that leave almost no margin for error. The pilot in the front seat misjudges the approach. The F-104 comes in too steep, too fast. It slams into the runway with catastrophic force. The front seat pilot survives, ejecting just before impact. Robert Lawrence in the back seat is killed instantly. Because MOL is classified, Lawrence's death receives minimal press coverage. Because MOL will be canceled in 1969 without ever flying a mission, Lawrence's selection as an astronaut isn't officially recognized for decades. He becomes a ghost, a man who trained for space, who died in the line of duty, but who doesn't appear in the official histories because acknowledging him would mean acknowledging the program he died for. Robert Lawrence should have been celebrated as a pioneer, as a trailblazer who broke barriers in one of the most exclusive and challenging fields in human history. Instead, he died in a classified program for a space station that never flew and spent 3 decades erased from the record. It wasn't until 2007, 40 years after his death, that NASA added Robert Lawrence's name to the Space Mirror Memorial at Kennedy Space Center. 40 years before the first African-American astronaut was officially acknowledged. 40 years of institutional amnesia, of convenient forgetting, of letting a hero fade into obscurity because remembering him would be complicated. Lawrence's erasure wasn't just about classification, it was about convenience. Acknowledging him would mean confronting NASA's own lack of diversity, admitting that the civilian space program had failed to select a black astronaut while the military had done so in 1967. It was easier to let him become a ghost. But Robert Lawrence wasn't the only astronaut whose death doesn't officially count. There was another pilot who actually made it to space and died on the way back down. The X-15 rocket plane is one of the most extraordinary aircraft ever built. Launched from under the wing of a B-52 bomber, powered by a rocket engine that burns ammonia and liquid oxygen, capable of speeds exceeding Mach 6 and altitudes above 50 miles. The X-15 bridged the gap between aviation and spaceflight. It was a research platform, a testbed for technologies that would later be used in the space shuttle, and a proving ground for pilots who wanted to touch the edge of space. 12 pilots flew the X-15 above 50 miles, the altitude the U.S. Air Force defined as the boundary of space. 8 of them received astronaut wings for those flights, officially recognized as astronauts by the military, even though they never orbited Earth, never flew a capsule, never launched on a rocket. One of those pilots was Major Michael James Adams. He was 37 years old, an Air Force test pilot, a man who had dreamed of flying higher and faster than anyone else. On November 15, 1967, he got his chance. Flight 3-65-97. Adams's 7th flight in the X-15 and his first attempt to reach space altitude. The mission profile called for a high-altitude zoom climb, light the rocket, point the nose up, and ride the momentum to the edge of the atmosphere before gliding back down. The ascent was perfect. Adams reached a peak altitude of about 266,000 feet, approximately 81 kilometers, well above the 50-mile threshold the U.S. military used to define space. For a few moments, Michael Adams was an astronaut, floating in the black sky above the curve of the Earth. But the descent went wrong. The X-15's control systems malfunctioned. The aircraft entered a hypersonic spin, tumbling end over end at speeds exceeding Mach 5. Adams fought to regain control, but the aerodynamic forces were too extreme. The X-15 broke apart at approximately 65,000 feet. Michael Adams died in the disintegration, his aircraft scattering across the Mojave Desert in thousands of pieces. He had reached space. He had earned his astronaut wings, awarded posthumously by the Air Force. But Michael Adams's death is not officially counted as a spaceflight fatality. Why? Because of an arbitrary line drawn in the sky. The U.S. military defines space as beginning at 50 miles, 80 kilometers. The Fédération Aéronautique Internationale, the international body that certifies aviation and spaceflight records, uses the Kármán line at 100 kilometers. Adams flew above the U.S. definition, but below the international one. And because the X-15 flights are generally treated as aeronautical research rather than spaceflight missions, because they didn't orbit, because they landed on runways like planes instead of splashing down in oceans like capsules, Adams's death exists in a bureaucratic limbo. He died during a mission to space. He earned astronaut wings, but he doesn't count. The definition problem is absurd, a technicality that erases a man's sacrifice because he died on the wrong side of an imaginary boundary. Michael Adams reached space, lost his life returning from it, and was quietly forgotten because his death didn't fit the narrative of what spaceflight was supposed to be. 8 men, 8 deaths between 1964 and 1968, in the years leading up to Apollo 11. Theodore Freeman, killed by a bird strike in a T-38. Elliot C. and Charles Bassett, killed in a fog-shrouded crash in St. Louis. Gus Grissom, Ed White, and Roger Chaffee, killed in the Apollo 1 fire. Robert Lawrence, killed in an F-104 crash while training for a classified space station. Michael Adams, killed when his X-15 broke apart during Reentry. Some of these deaths were freak accidents, acts of God that no amount of preparation could have prevented. But most were systemic failures, the result of an agency and a nation pushing too hard, moving too fast, ignoring warning signs in a desperate race against the Soviet Union. They were the cost of Cold War hubris, of a space program that valued speed over safety, secrecy over transparency, the mission over the men. And they were erased, not with malice, not through conspiracy, but through the quiet bureaucracy of institutional forgetting. Their deaths were ruled training accidents instead of spaceflight fatalities. Their programs were classified. Their names were left off memorials for decades. They became ghosts, shadows, footnotes in a story that preferred to remember only the triumphs. But here's the truth that NASA eventually had to learn. You can't reach the moon without acknowledging the cost. Every triumph in the space race was built on lessons written in blood. Theodore Freeman's death taught NASA about the risks of high-performance jet training. C and Bassett's crash revealed the dangers of pushing schedules in bad weather. The Apollo 1 fire forced a complete redesign of the spacecraft, implementing safety measures that made lunar missions possible. Robert Lawrence and Michael Adams died in programs that pushed the boundaries of what humans could survive, testing technologies and procedures that would later save lives. Their deaths weren't meaningless. They weren't just tragic accidents to be swept under the rug and forgotten. They were the foundation upon which Apollo 11 was built. Every safety protocol, every design change, every lesson learned came from someone who didn't come home. On July 20th, 1969, when Neil Armstrong stepped onto the lunar surface and spoke those famous words, "That's one small step for man, one giant leap for mankind," he was walking on ground that 8 other men had died trying to reach. Their names should have been on his lips. Their faces should have been in the mission patch. Their sacrifice should have been acknowledged in that moment of triumph. Instead, they became the Shadow Astronaut Corps, the men who paid for the moon landing with their lives and then vanished from history. But they're not forgotten anymore. Their names are slowly being added to memorials, their stories finally being told. Because the truth about the space race isn't just about triumph and courage and American ingenuity. It's also about cost, about sacrifice, about the men who died so that others could succeed. 8 men, 8 deaths, 8 names that should be as famous as Armstrong, Aldrin, and Collins, Theodore Freeman, Elliot C., Charles Bassett, Virgil Grissom, Edward White, Roger Chaffee, Robert Lawrence, Michael Adams. Remember them, because they paid for the stars with their lives, and they deserve more than silence. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.
At lunar return speed, the Apollo command module slammed into the top of Earth's atmosphere at roughly 36,000 feet per second, about 11 kilometers per second, or nearly Mach 33. On Apollo 4, the unmanned test that simulated a lunar return profile, instruments recorded 36,545 feet per second at entry interface with a flight path angle of -6.93 degrees. That is the fastest any American spacecraft had ever flown into the atmosphere at that time. Entry interface was defined at 400,000 feet, approximately 122 kilometers, the altitude where the atmosphere first became dense enough for the blunt body to generate meaningful drag and lift. From that point on, the vehicle's trajectory was dominated by aerodynamics, not thruster authority. The guidance system had to arrive at that boundary with the heat shield already pointed forward, the angle of attack already near its trim value, and the lift vector already correctly oriented. There was no time to improvise after hitting the atmosphere. Any significant attitude error at interface would immediately tilt the lift vector, change the effective flight path angle, and push the trajectory out of a corridor that was only a few tenths of a degree wide. Too shallow, and the capsule could skip back into space. Too steep, and deceleration and heating would exceed both structural and human limits. This is why the orientation maneuver before entry interface was not a convenient step. It was a precondition for survivable heating, acceptable G-loads, and accurate targeting of the splashdown point. If you're interested in the real story behind space programs, the technology that actually flew, are the decisions that never made the press releases, and how space became a strategic domain. Subscribe to Space Cluster, like and turn on notification. We focus on what was built, why it mattered, and where it really led. Now, back to the story. The Apollo command module was not a symmetric ballistic sphere. It was a blunt cone with an intentionally offset center of mass. The mass center was displaced from the vehicle's geometric axis, shifted roughly 8 inches along the symmetry axis relative to the aerodynamic center of pressure. This offset was a deliberate engineering choice and extensive wind tunnel and free flight testing validated the trim behavior it produced. That offset generated a small but decisive aerodynamic moment during entry, or the moment trimmed the capsule to a fixed negative angle of attack, a pre-flight design value of about -6.5 degrees, corresponding to a total angle of attack of 156.84 degrees as measured from the back of the heat shield. Flight data later confirmed this matched closely, though early hypersonic trim came in roughly 1.5 degrees lower than pure wind tunnel predictions. This was expected. No ground facility at the time could perfectly replicate the combination of high Mach number and low Reynolds number the capsule experienced in the first moments of entry. Apollo 4 became the real validation test. At this trim angle, the capsule's lift-to-drag ratio was roughly 0.3. Wind tunnel work predicted this, and flight-derived data came in about 10% higher than wind tunnel values in the early hypersonic regime, converging linearly down to about Mach 6. A lift-to-drag ratio of 0.3 does not sound like much, but with drag at peak deceleration on the order of several g, that ratio translated into a lift force of roughly a couple of g, enough to curve the flight path substantially through the upper atmosphere. This gave Apollo something remarkable for a blunt capsule: genuine controllable lift. By rolling the capsule around its velocity vector, the guidance system could point that lift vector up or down relative to the local vertical, trading altitude for range and shaping the deceleration profile. That lift-to-drag ratio of 0.3 to 0.4 enabled a downrange footprint of 2,000 to over 5,000 nautical miles and cross-range control of roughly 100 to 200 nautical miles through 4 or 5 bank reversals during descent. All of this depended on one thing: the command module reaching entry interface, already heat shield forward and already oriented so the offset mass could produce the intended trim angle. A misoriented capsule would not present the correct geometry to the flow, and the carefully designed relationship between mass distribution, angle of attack, lift, and drag would collapse. Apollo's entry guidance did not treat the atmosphere as a simple drag brake. It treated it as a controllable medium where lift was used to stay inside a narrow corridor in flight path angle and dynamic pressure while meeting a downrange target. The onboard guidance logic computed a reference trajectory that satisfied constraints on maximum deceleration, maximum heating rate, and range to the landing area. Given the initial state at entry interface, position, velocity magnitude, and direction, the algorithm synthesized an ideal profile of velocity versus altitude and commanded bank angle to follow it. A secant-type iteration scheme computed the reference trajectory for the skip or lifting entry profile, searching for the bank angle magnitude that would produce the required integrated deceleration and altitude history. The guidance operated in distinct phases. At the onset of measurable drag, roughly 0.05 g, the system entered initial entry, monitoring sensed acceleration to confirm atmospheric contact. It then transitioned to the hunt test phase, targeting a constant drag level to establish the vehicle on its reference profile. From there, up control took over, managing the pull-up portion of the trajectory, adjusting lift to control the altitude rate and keep the vehicle within the deceleration corridor. Finally, the system shifted to its final phase for terminal range control, driving toward the splashdown coordinates. Bank angle magnitude determined how strongly the lift vector curved the path. Its sign, left or right roll, controlled cross range and was reversed according to bank reversal logic that kept the vehicle within lateral bounds while still hitting the intended downrange target. These bank reversals did not change the magnitude of lift, but flipped its lateral component, effectively zigzagging the trajectory within a corridor centered on the great circle path to the landing point while keeping the vertical component of lift consistent with the desired deceleration pattern. The corridor itself represented a balance. Too shallow a flight path angle produced long skip-like trajectories with low peak G, but high integrated heating. Too steep produced high deceleration and heating, but short range. Apollo's guidance solution aimed to start near the center of this corridor and then modulate lift to keep the trajectory between preset shallow and steep boundaries. On Apollo 4, the entry was steep enough that the vehicle skipped to an altitude of 241,000 feet, bypassing the guidance's Kepler prediction phase entirely. A near miss that demonstrated just how narrow the margins were. To execute all of this, the system needed an accurate inertial state vector. At the moment, it began serious aerodynamic interaction, and a capsule already oriented so that its lift and drag matched the aerodynamic models built into the guidance law. The transition from deep space coast to atmospheric flight began with the last mid-course correction on the return leg. That burn cleaned up residual targeting errors so that if the entry guidance performed nominally, the capsule would intersect the entry interface sphere at the correct velocity and entry angle to fall inside the guidance envelope. Following trans-lunar injection and subsequent maneuvers, the inertial measurement unit's stable platform was periodically realigned using star sightings, with the crew measuring angles between known stars and the spacecraft axis, then driving the platform to match a computed inertial attitude tied to the celestial frame. A final star sightings held IMU errors to less than 0.05 degrees. Critical precision, because any large inertial error would propagate into entry angle and range errors that lift modulation might not be able to correct. Before committing to the re-entry corridor, the crew and ground checked that the IMU alignment and guidance state were within tolerances. This chain, star sightings to platform alignment, platform to body attitude to velocity vector, was what preserved attitude knowledge at the moment of atmospheric commitment. During much of trans-lunar coast, the vehicle executed passive thermal control, a slow, continuous rotation, often called the barbecue roll, to distribute solar heating evenly and keep propellant and structure within acceptable temperature ranges. That slow roll intentionally degraded attitude knowledge in the vehicle body axis, but inertial attitude relative to the stars remained well-defined, and the system could always return to a precise orientation by maneuvering relative to the platform. At a specified time before entry, passive thermal control was terminated and the spacecraft was stabilized. Only then could the guidance system and crew set and hold the exact attitudes needed for the next critical steps: service module separation and the entry orientation maneuver. Well before significant aerodynamic loads, on the order of 30 to 60 minutes before the capsule reached 400,000 feet, with timing tailored to each mission's geometry, the combined command and service module stack had to be broken apart. On Apollo 14, for example, separation occurred roughly 40 minutes before entry interface. The service module carried the main propulsion system, fuel cells, and most consumables, but it had no heat shield. Its mass and structure could not survive entry and would destroy the command module if it remained attached. Explosive devices released the physical connections, and separation velocity drove the service module clear of the command module's eventual entry path. Once the service module was gone, the command module's mass properties changed radically. The center of mass shifted into its designed heat shield forward entry position. The reaction control system on the command module now had to manage all attitude control alone. Service module jettison also reduced the vehicle's moment of inertia significantly, making it more responsive to RCS torques, but also more sensitive to disturbances. During entry, the command module would consume roughly 90 pounds of RCS propellant, while total mass decreased by about 210 pounds, accounting for both ablative material loss and propellant expenditure. From that point onward, there was no high-thrust propulsion and no large structural inertia to damp unwanted rotation. Attitude during entry would depend entirely on the small thrusters and the aerodynamic stabilizing effect of the offset mass in the flow. After separation, the command module was initially oriented with the blunt heat shield facing roughly along the previous plus x-axis of the combined stack, which had been pointed near the velocity vector during much of the return flight. To re-enter, the capsule had to be rotated so that the heat shield pointed directly into the oncoming flow, and with the proper pitch attitude corresponding to its trim angle of attack. This was achieved with a 180-degree pitch-around maneuver, commanded through the Command Module's RCS, under control of the Guidance and Navigation System's digital autopilot, or, as a backup, by the crew using manual rotational hand controllers. The digital autopilot used rate and attitude error feedback to fire combinations of RCS thrusters, executing the maneuver at a controlled rate of roughly a quarter degree per second to avoid structural loads and conserve propellant. Attitude was referenced to the IMU's stable platform, which still defined a precise inertial frame. The guidance logic or crew procedures specified the target orientation relative to this frame, converting desired angles to gimbal coordinates so the digital autopilot could drive the vehicle from its pre-separation orientation to the heat shield forward entry attitude. Because the command module's aerodynamic trim depended on the alignment of the offset center of mass with the flow, the pitch-around had to place the capsule within a small angular tolerance of the intended attitude by the time it reached entry interface. Any residual error would effectively change the angle of attack, altering both lift and drag coefficients from their modeled values and degrading the guidance system's predictions. The 180-degree maneuver therefore represented not just a geometric reversal, but a calibration step, where the spacecraft moved from a propulsion-dominated orientation regime into the configuration for which the entry aerodynamics and guidance laws had been designed. The command module's RCS was arranged in clusters around the capsule to provide full 3-axis control using small monopropellant thrusters. These jets generated moments about pitch, yaw, and roll axes sufficient to reorient the much lighter post-separation command module, and then hold attitude against small disturbances while the atmosphere was still thin. During the final approach to entry interface, the digital autopilot maintained attitude within a defined deadband, firing jets in short pulses whenever sensed attitude or rate departed from the commanded set. Gain settings, maximum allowed rates, and deadbands were all chosen to ensure that the RCS could achieve the necessary maneuvers without saturating propellant use or inducing excessive rotational rates just as the capsule hit the atmosphere. As dynamic pressure built up, aerodynamic torques quickly began to dominate over RCS torques, especially in pitch and yaw. The offset center of mass created a natural restoring moment toward the trim angle of attack, effectively integrating the aerodynamics into the control loop and reducing RCS demand for pitch and yaw stability. Roll control remained an RCS task throughout. Rolling the capsule about its symmetry axis did not significantly change the angle between the offset mass vector and the oncoming flow. This allowed the guidance system to use roll commands to steer the lift vector without fighting large restoring moments in pitch and yaw, making roll a clean control variable for trajectory shaping. The Apollo guidance computer ran dedicated entry programs that generated bank angle commands designed to drive actual altitude and velocity toward the reference trajectory while staying within load limits. The computer did not directly fire individual thrusters. It produced guidance commands, attitude targets, bank reversals, mode transitions, that the digital autopilot translated into jet firings. This separation between high-level guidance law and low-level control made the system robust and allowed manual backup intervention at the control level if needed. The crew could in principle fly entry manually by monitoring the flight director attitude indicator, the G-meter, and rate displays, selecting bank angles and commanding roll directly through the hand controllers. But this was a last resort. The corridor was narrow enough and the dynamics fast enough at hypersonic speed that sustained manual control would have been extremely demanding even for highly trained test pilots. As the capsule plunged deeper into the atmosphere and deceleration climbed, the shock layer around the heat shield ionized the surrounding air. This created a sheath of plasma that blocked all radio communications with the ground, a phenomenon known as ionization blackout. For Apollo lunar returns, blackout lasted roughly 3 to 4 minutes. During that window, Mission Control had no telemetry, no voice contact, and no way to know whether the guidance was performing correctly. The crew was entirely on their own, monitoring the flight director attitude indicator and the G-meter for any sign that the bank program was deviating from plan. Under nominal conditions, no manual takeover was needed. But if something had gone wrong during blackout, the crew would have had to diagnose and respond without any ground support. When communications resumed after blackout, it was one of the most closely watched moments in every Apollo mission. Confirmation that the capsule had survived peak heating and peak deceleration and was on a trajectory toward the recovery fleet. The narrowness of the entry corridor is easiest to appreciate through its failure modes. So if the capsule arrived at entry interface with the heat shield not fully forward, or with the angle of attack shallower than planned, the effective lift vector could raise the trajectory and reduce deceleration too much, causing the vehicle to skim the upper atmosphere and skip back toward space. A skip out might not mean immediate loss, but it would leave the capsule on a new trajectory with reduced energy and altered geometry, outside the pre-planned guidance envelope, and perhaps beyond the remaining lift and control authority to deliver to the target area. It would also increase total heating because of the extended time spent at high speed in thin but non-negligible atmosphere. If the attitude error drove the effective angle of attack steeper than nominal, yet the vehicle could descend more quickly into denser air, with less opportunity to use lift to manage deceleration. This would raise peak G loads and heating rates, and could challenge structural and physiological limits, even if the heat shield material itself had design margin. A loss of roll control would remove the primary way the guidance system modulated lift. The capsule would fly a nearly fixed bank trajectory, with range and lateral errors growing beyond planned limits. Failures in the inertial reference, a misaligned platform or incorrect star update, would appear as systematic biases in attitude. The computer could still compute and command bank angles, but the real relationship between body roll and lift direction would no longer match the model. Apollo 13 demonstrated the most dramatic variation on these failure modes. With the service module severely damaged, the crew had to jettison it earlier than planned and use the lunar module as a lifeboat. With the command module powered down to conserve batteries, the normal computer-driven alignment and attitude setup was impossible. The crew had to manually set the entry attitude using backup procedures under extreme power constraints, one of the most impressive feats of crew resourcefulness in the entire program. They made it, but the margins were thinner than anyone would have liked. Each of these failure modes ties directly to the correctness of the pre-entry orientation maneuver. If the command module did not arrive at entry interface with the heat shield forward, the trim angle established, and the bank axis known, or the entry guidance logic would be working from false premises, and the corridor it believed it was flying would no longer be the corridor the vehicle was actually in. In principle, one could imagine delaying the final attitude cleanup until the capsule was closer to the sensible atmosphere. In practice, this would have been unacceptable. The onset of aerodynamic forces at hypersonic speed left almost no time to correct large orientation errors before loads built up and the guidance law began integrating its feedback. The sequence: terminate passive thermal control, separate the service module, perform the 180-degree pitch around, verify attitude, then enter the atmosphere, created a buffer between the last controllable vacuum-like conditions and the first strong aerodynamic torques. That buffer was the only time available to troubleshoot without fighting increasing dynamic pressure. Apollo's re-entry orientation maneuver was more than a geometric repointing of a capsule. It was the moment when every major system, propulsion, guidance, mass distribution, control, and crew procedure had to converge on a single coherent state. The mass offset only produced the intended lift-to-drag ratio if the capsule reached entry interface with the correct angle of attack. The heat shield only met its thermal assumptions if it faced the flow within narrow angular limits. The reaction control system only had authority to place and hold that orientation if separation, autopilot logic, and thruster health all aligned in time. The guidance algorithms only produced the right bank commands if their internal picture of attitude and energy matched reality. And the crew's procedures, ending thermal control, confirming platform alignment, arming separation, monitoring the pitch around, watching for the first cues of deceleration, were the human link closing the loop, ready to intervene if any component diverged from plan. All of this was compressed into the minutes leading up to and just beyond 400,000 feet and 36,000 feet per second, when the capsule crossed from vacuum dynamics into hypersonic aerodynamics. Re-entry orientation was Apollo's final systems integration test, run once per mission with no opportunity to repeat. A blunt body with a small lift vector, steered by precise attitude control through a narrow corridor, turning deep space velocity into a controlled arrival at Earth. If you appreciate detailed Apollo engineering breakdowns like this, consider joining the channel. Your support helps fund deeper research and keeps these technical deep dives coming. Thanks for watching. On Christmas Eve 1968, 3 men orbited the moon and read from the Book of Genesis to a billion people listening on Earth. The images they brought back, particularly the iconic Earthrise photograph, became symbols of human achievement and perspective. Apollo 8 was celebrated as a triumph of courage and engineering, the mission that proved humans could leave Earth orbit and survive the journey to another world. But that was the public story. The real story of Apollo 8 begins not in Houston or at Cape Kennedy, but in the windowless rooms of the National Reconnaissance Office and the CIA's Office of Scientific Intelligence. It begins with grainy photographs taken by Soviet tracking stations, with intercepted telemetry data, and with a growing alarm among American intelligence analysts about what the Soviets were preparing to do. If you're interested in the real story behind space programs, the technology that actually flew, the decisions that never made the press releases, and how space became a strategic domain, subscribe to Space Cluster, like and turn on notification. We focus on what was built, why it mattered, and where it really led. Now, back to the story. In August 1968, NASA made a decision that shocked even its own engineers. Apollo 8, originally planned as an Earth orbital test of the lunar module in early 1969, would be completely redesigned. The lunar module would be removed entirely. Instead, the mission would send 3 astronauts to lunar orbit in December, just 4 months away. It would be only the second crewed flight of the Saturn V rocket, and the first time humans would leave the protective shield of Earth's magnetosphere. The official explanation was straightforward. The lunar module was behind schedule. Grumman was having problems with the ascent engine and the landing gear. Rather than waste time with another Earth orbital mission, NASA would leap forward, test the command and service module in deep space, practice lunar orbital navigation, scout landing sites for future missions, beat the Soviets to the moon, even if it was just to orbit it. This explanation was true, but it was not complete. Throughout 1968, American intelligence had been tracking a series of Soviet spacecraft launches under the designation Zond. These were not the familiar Soyuz capsules that orbited Earth. These were something different. Zond 4 had been launched in March, reaching a distance of 186,000 miles from Earth before returning. The mission ended in failure when the capsule's guidance system malfunctioned and the spacecraft had to be destroyed during re-entry. But the intent was clear. The Soviets were testing a circumlunar trajectory. Then came Zond 5 in September 1968. This mission succeeded. The spacecraft looped around the moon, photographed the far side, and returned to Earth. The capsule splashed down in the Indian Ocean and was recovered by a Soviet naval vessel. On board were biological specimens, wine flies, mealworms, plants, seeds, bacteria, and 2 Russian tortoises. All survived. The message was unambiguous. The Soviet Union had demonstrated a spacecraft capable of sending living creatures to the moon and bringing them back alive. Inside the National Security Council, the implications were being carefully assessed. The Zond spacecraft was a stripped-down version of the Soyuz, modified for a single purpose: a quick circumlunar flight. American analysts knew it could not land on the moon. It lacked the necessary propulsion and life support for a long-duration mission. But it could carry a single cosmonaut around the moon and return him to Earth as a hero. The first human to see the far side with his own eyes, the first human to leave Earth orbit. Another devastating propaganda victory for the Soviet Union, coming just months after the crushing of the Prague Spring, had reminded the world of the iron fist inside the velvet glove. This was the context in which NASA Administrator James Webb and Flight Director Chris Kraft presented the Apollo 8 proposal to Administrator Thomas Paine in August. This was the context in which Paine approved a mission profile that violated nearly every principle of incremental testing that had governed the space program since Mercury. This was why Frank Borman, Jim Lovell, and Bill Anders found themselves training for a mission that did not exist 6 weeks earlier. But there was another dimension to the urgency, one that remained classified for decades after the mission flew. The far side of the moon is unique in the solar system. Because the moon is tidally locked to Earth, the same hemisphere always faces our planet. The opposite hemisphere, the far side, never does. This creates a zone of permanent radio silence. No television broadcasts, no military communications, no radar installations, no electronic noise of any kind from Earth can reach the far side. It is the most radio-quiet location within easy reach of human technology. For signals intelligence purposes, this makes it invaluable. Soviet interest in the far side had been evident since Luna 3 photographed it in 1959. Those first blurry images revealed a landscape dramatically different from the near side. Heavily cratered, almost devoid of the dark Maria that characterized the face of the moon visible from Earth. Throughout the 1960s, Soviet scientists published papers discussing the scientific value of a radio telescope on the far side, shielded from Earth's electromagnetic interference. Some of these papers appeared in open scientific journals. Others were noted in classified intelligence assessments for their potential dual-use applications. A radio telescope on the far side could observe frequencies completely drowned out by human activity on Earth. But it could also intercept communications that its operators did not want anyone on Earth to know they were monitoring. Signals from American satellites, telemetry from missile tests, communications between naval vessels. All of this could be received, recorded, and relayed back to Earth without any possibility of detection or jamming from ground-based sources. The National Reconnaissance Office understood this. So did the National Security Agency. And so, when Zond 5 successfully demonstrated a lunar flyby capability, the question became urgent. What if the next step was not a propaganda stunt, but a reconnaissance mission? What if the Soviets were planning to place instruments on the far side, not for science, but for intelligence collection? Apollo 8's mission plan included extensive photography of the lunar surface. The official purpose was site selection for future landings. The astronauts would use a Hasselblad 500 EL camera with a 250mm lens to photograph potential landing zones in the equatorial regions. This was true. But the mission profile also called for photography of the far side, particularly the polar regions and the areas of highest elevation. These photographs had a secondary purpose that was not discussed in press conferences. They constituted the first strategic survey of potential sites for a listening post. Areas with line of sight to Earth for relay purposes. Regions with thermal characteristics suitable for long-term equipment survival. Terrain features that could provide natural shielding or support for antenna structures. All of this information would be valuable if the United States ever decided to place its own installations on the far side. And all of it would be necessary to understand what the Soviets might be planning if they got there first. Frank Borman understood this dimension of the mission. As a former Air Force pilot and instructor at the Aerospace Research Pilot School, he had security clearances that extended beyond the normal scope of astronaut activities. His pre-flight briefings included discussions that did not appear in the mission transcripts released to the public. He knew that some of the photography he would conduct had customers beyond the Manned Spacecraft Center in Houston. On December 21, 1968, Apollo 8 lifted off from Launch Complex 39A at Cape Kennedy. The Saturn V performed flawlessly, placing the spacecraft into Earth orbit. 2 hours and 50 minutes later, the SIVB third stage reignited for the trans-lunar injection burn. For the first time in history, humans were leaving the gravitational dominance of Earth. The 3-day coast to the moon was uneventful. The crew conducted navigation checks, photographed Earth, and prepared for lunar orbit insertion. On December 24th, as the spacecraft swung behind the moon and lost radio contact with Earth, the Service Propulsion System engine fired for 4 minutes and 7 seconds, slowing Apollo 8 into an elliptical lunar orbit ranging from 60 to 169 miles altitude. When the spacecraft emerged from behind the moon and re-established contact, the first words transmitted were purely technical: confirmation of orbital parameters, system status, fuel remaining. But the subtext was historic. 3 humans were orbiting another world, and they had just become the first to see something no human had ever witnessed: Earthrise over the lunar horizon. Over the next 20 hours, the crew completed 10 orbits of the moon. They conducted the planned photography of potential landing sites: the Sea of Tranquility, where Armstrong and Aldrin would land 7 months later, and several backup locations. They photographed the far side in detail, capturing images of craters and highlands that had only been seen before in the low-resolution photographs from robotic probes. They also photographed areas that were not on the public mission timeline. The orbital mechanics of Apollo 8 were dictated partly by the need to return to Earth, partly by lighting conditions for photography, and partly by coverage requirements. The orbit was designed to provide visibility of specific regions during specific passes. Some of these regions were selected by geologists. Others were selected by analysts with different priorities. After the mission, the photographs were cataloged and distributed. Many went to the United States Geological Survey in Flagstaff, Arizona, where they were used to construct detailed maps for landing site selection. Others went to different agencies, where they were analyzed for different purposes. The resolution was not high enough for detailed terrain analysis, but it was sufficient for broad strategic assessment. Sufficient to identify potential sites. Sufficient to understand what would be required to place equipment there. Sufficient to recognize such equipment if it appeared in future reconnaissance imagery. Zond 6 launched on November 10, 1968, just weeks before Apollo 8. It successfully circled the moon and returned to Earth, but the landing was catastrophic. The cabin depressurized during re-entry, and the parachute deployed prematurely, causing the capsule to crash. If cosmonauts had been aboard, they would have died. The Soviets continued to insist publicly that they had no plans for a crewed circumlunar flight. But American intelligence knew better. The biological payloads on Zond 5 and the continued test flights made Soviet intentions clear. After Apollo 8's success, the Soviet circumlunar program lost its purpose. There was no propaganda value in being second. Zond 7 flew in August 1969, after Apollo 11 had already landed on the moon. It was a perfect flight, demonstrating that the Soviets had finally solved the re-entry problems. But by then it did not matter. The political moment had passed. What did not pass was the strategic interest in the far side. Throughout the 1970s, both American and Soviet scientists continued to publish papers about the scientific value of far-side installations. The Soviets proposed elaborate plans for radio telescopes that would be serviced by cosmonauts from a nearby base. NASA studied concepts for automated instrument packages that could be delivered by Apollo-derived vehicles. None of these plans were implemented, but the studies continued. In the 1990s, after the end of the Cold War, some of these studies were declassified. They revealed that both sides had seriously considered the military applications of lunar installations. Not weapons platforms, the Outer Space Treaty of 1967 prohibited that, but reconnaissance and communications facilities. The far side was particularly attractive because it offered something that no satellite in Earth orbit could provide: a stable platform completely immune to electronic interference from Earth with unlimited line of sight to half the sky. The intelligence value of such a facility would be extraordinary. A signals intelligence station on the far side could intercept communications from satellites that its operators on Earth could not even detect, because the satellites would be below the horizon. It could monitor deep space communications from interplanetary probes, potentially gathering technical intelligence about propulsion systems, guidance algorithms, and mission profiles. It could serve as a relay station for covert communications, using the moon itself as a shield against detection. None of this was science fiction. The technology existed in the 1970s. The only barriers were cost and political will. Apollo 8's photography provided the foundation for understanding where such facilities could be placed and what would be required to build them. The mission's strategic reconnaissance value was never publicly acknowledged, but it was real. The photographs that appeared in National Geographic and on posters in classrooms around the world were the same photographs that appeared in classified briefing books at the National Reconnaissance Office. This dual purpose was not unique to Apollo 8. Every Apollo mission carried cameras and film specifications that were influenced by requirements from the intelligence community. The high-resolution mapping camera flown on later missions had performance characteristics that exceeded what was necessary for landing site selection, but were entirely appropriate for strategic reconnaissance. The orbital ground tracks were planned to provide coverage of areas that had scientific interest and other kinds of interest. None of this diminishes the courage of the astronauts or the achievement of the engineers who made the missions possible. But it adds a layer of context that is missing from the popular narrative. Apollo was not purely a scientific endeavor or a symbolic gesture. It was also an instrument of national power, and it was used as such. The Christmas Eve broadcast from lunar orbit, in which the crew read from Genesis, is remembered as a moment of unity and inspiration, and it was. But it was also a demonstration of capability, a message to Moscow and to the world that the United States had achieved something the Soviet Union had failed to do, despite years of effort and despite getting there first with robotic probes. The tragedy of Apollo 8's shadow history is not that it served strategic purposes. The tragedy is what did not happen afterward. The reconnaissance data was collected, the sites were identified, the technical requirements were understood, but the installations were never built. The far side remains as radio quiet today as it was in 1968. But now that silence is threatened by plans for commercial lunar development and satellite constellations that will fill even the far side with radio noise. The window of opportunity for a truly isolated listening post is closing. In another decade, there may be no place in the inner solar system that is free from human-generated electromagnetic interference. The unique strategic and scientific value of the far side will be lost, not because we lacked the capability to exploit it, but because we lacked the will. This is the pattern that repeats throughout the shadow history of the space race. Extraordinary capabilities developed at enormous cost, then abandoned before their full potential could be realized. Intelligence gathered, analyzed, filed away, and forgotten as political priorities shifted and budgets were cut. Apollo 8 proved that humans could travel to the moon and return safely. It provided the confidence needed to attempt a landing. It delivered strategic intelligence about potential far-side installations, and then, like so much of the Apollo program, it became a memory. The capability was demonstrated once and then allowed to atrophy. The Saturn V production lines were closed. The infrastructure was dismantled. The knowledge was retained only in aging documents and the fading memories of the engineers who built it. Today, as new powers plan their own lunar programs, the strategic questions that motivated Apollo 8's rushed schedule are relevant again. China has landed multiple probes on the far side, using a relay satellite to communicate with Earth. Their stated intentions are scientific, and there is no reason to doubt this. But the capability they are demonstrating has obvious dual-use potential. A relay satellite that can support a rover can support other kinds of payloads. A landing capability that can deliver scientific instruments can deliver other kinds of instruments. The photographs that Frank Borman, Jim Lovell, and Bill Anders took in December 1968 are still being studied. Not by historians or space enthusiasts, but by analysts planning for scenarios that may unfold in the next decade. The strategic value of the far side has not diminished. If anything, it has increased as Earth orbit becomes more congested and more contested. Apollo 8 was sold to the public as a journey of exploration and inspiration. And it was. But it was also a reconnaissance mission, flown on an accelerated schedule because of intelligence about Soviet capabilities and concerns about Soviet intentions. The astronauts who flew it were not just explorers. They were also, whether they fully understood it at the time, intelligence collectors. This does not diminish their achievement. If anything, it adds weight to it. They were carrying out multiple missions simultaneously, serving multiple purposes under conditions of extraordinary risk. The fact that some of those purposes remained classified for decades does not make them less real or less important. What remains is the question of what we do with the knowledge they brought back. The far side of the moon is still there, still radio quiet, still offering unique capabilities for both science and intelligence. The photographs from Apollo 8 still show the same craters, the same highlands, the same potential sites. The technology to return there exists, though it must be rebuilt. The question is whether we have the strategic vision to recognize what was understood in 1968, that some places have value not just for what they are, but for what they enable. Apollo 8 gave us the first human perspective on that value. What we choose to do with that perspective will determine whether the mission's shadow history remains just history or becomes prologue to something new. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching. At 5 minutes and 17 seconds into the Apollo 13 mission, the center engine of the Saturn V second stage shut down. 2 minutes and 12 seconds early. Automatic, unplanned. The mission continued on 4 engines instead of 5, and nobody outside mission control knew anything had gone wrong until much later. Because 3 days after that, an oxygen tank exploded, and suddenly nobody cared about an engine shutdown during ascent. But here's what matters. That center engine shutdown wasn't a minor glitch. It was a symptom of the same problem that nearly tore a Saturn V apart 2 years earlier. A problem so severe that NASA considered canceling the entire Apollo program. A problem that the best aerospace engineers in America spent months solving, implementing a fix so elegant it seemed to work perfectly. Until Apollo 13, when it came back. The problem has a name: pogo oscillation. And if you've never heard of it, that's exactly the point of this story. If you're interested in the real story behind space programs, the technology that actually flew, the decisions that never made the press releases, and how space became a strategic domain, subscribe to Space Cluster, like, and turn on notification. We focus on what was built, why it mattered, and where it really led. Now, back to the story. On April 4th, 1968, Apollo 6 lifted off from Kennedy Space Center. Unmanned, the second and final test of the complete Saturn V stack before NASA would trust it with human lives. The first 2 minutes went perfectly. The 5 F1 engines of the first stage burned exactly as designed, generating 7.5 million pounds of thrust. A stage separation occurred on schedule. The 5 J2 engines of the second stage ignited, and then the entire rocket began to shake itself apart. The oscillation started at around 200 seconds into the flight. The vehicle began experiencing vertical accelerations of plus or minus 0.6 g at a frequency of roughly 5 Hz. To be clear about what that means, the rocket was bouncing up and down 5 times per second with enough force that if astronauts had been aboard, they would have been slammed against their restraints hard enough to cause injury. The instrument unit recorded structural loads approaching design limits. Panels separated from the spacecraft adapter. The entire vehicle was entering a resonance condition that, if it continued, would result in catastrophic structural failure. The phenomenon is called pogo oscillation, named for its resemblance to bouncing on a pogo stick. But the mechanism is far more complex and far more dangerous than the toy suggests. Here's what happens. A rocket engine creates thrust by burning propellant and expelling it through a nozzle. The flow of propellant from the tanks to the combustion chamber travels through feed lines and pumps. These feed lines have natural resonant frequencies, just like any mechanical system. When the thrust from the engine creates vibrations in the vehicle structure, those vibrations travel back through the structure to the propellant tanks. The vibrations cause pressure waves in the liquid propellant. Those pressure waves travel through the feed lines to the engine. The engine responds to the pressure variations by producing variations in thrust. Those thrust variations create more structural vibrations, and the cycle reinforces itself. It's a feedback loop. And like all feedback loops, if the frequency of the oscillation matches the natural resonant frequency of the system, the amplitude grows exponentially. The rocket literally shakes itself to pieces. Apollo-6 survived, barely. The pogo oscillations damaged 2 of the 5 J2 engines on the second stage. When the third stage ignited for the translunar injection, burn simulation, one of its systems failed due to damage sustained during the second stage pogo event. The mission achieved orbit, but it was a failure by every measure that mattered. NASA could not put astronauts on a rocket that behaved like this. The problem wasn't new. Pogo oscillations had been observed in Titan II missiles. The Gemini program, which flew on Titan II, had experienced pogo events severe enough that astronauts reported difficulty reading instruments and operating controls. But the Titan II had 2 engines. The Saturn V second stage had 5 J2 engines, each producing 232,000 pounds of thrust, all fed from common propellant tanks through a complex manifold system. The scale and complexity made the problem orders of magnitude worse. NASA established a pogo task force immediately after Apollo-6. Engineers from Marshall Space Flight Center, Rocketdyne, North American Aviation, and Boeing converged on the problem. They had months, not years. Apollo 8 was scheduled for December, and it needed to work. The political pressure was immense. The Soviet Union's Zond program was attempting circumlunar flights. If NASA couldn't fix pogo, the moon might slip away. The team approached the problem from first principles. They built detailed mathematical models of the propellant feed system, mapping every resonant frequency. They conducted static test fires with instrumentation measuring thrust variations, pressure oscillations, and structural vibrations at hundreds of points simultaneously. They filled water tanks with the same geometry as the propellant tanks and used them to study fluid dynamics under oscillation. The data revealed something critical. The pogo oscillation on Apollo-6 occurred at 5.2 Hz, which corresponded almost exactly to a resonant mode in the liquid oxygen feed system. The solution they developed was deceptively simple. Install a cavity filled with helium gas in the liquid oxygen feed line, just upstream of the pre-valve. The helium cavity acts as a shock absorber. When a pressure wave travels up the feed line from the engine, it hits the helium gas. Gas compresses far more easily than liquid, so the helium absorbs the pressure spike, preventing it from propagating back to the tank. The pressure wave dissipates as heat in the compressed gas. The feedback loop is broken. The engineering was anything but simple. The helium cavity had to be precisely sized. Too small, and it wouldn't absorb enough energy. Too large, and it would affect propellant flow rates and engine performance. The cavity had to maintain its helium charge throughout the fueling process and the hours of countdown. It had to operate in cryogenic temperatures, under high vibration, and in the vacuum of space. The pre-valve timing had to be adjusted to account for the slight delay the cavity introduced in propellant flow. A Rocketdyne team led the development of the helium injection system. They conducted over 40 test fires at the Santa Susana Field Laboratory, refining the cavity volume, the helium pressure, and the injection timing. By October 1968, they had a solution they believed would work. It was installed on the Saturn V for Apollo 8. Apollo 8 launched on December 21, 1968. The pogo suppression system worked. The second stage burn was smooth. Frank Borman, Jim Lovell, and Bill Anders became the first humans to leave Earth orbit, circle the moon, and return safely. The fix held for Apollo 9. It held for Apollo 10. It held for Apollo 11. Neil Armstrong and Buzz Aldrin walked on the moon. The pogo problem was solved. Except it wasn't. April 11, 1970. Apollo 13. 5 minutes and 17 seconds after launch, the center engine of the second stage shut down automatically. The shutdown was triggered by the engine's thrust chamber pressure sensor, detecting oscillations exceeding safe limits. Pogo oscillations. In the center, J2 engine. The same problem that had been solved 2 years earlier. Here's what happened. The helium injection system worked perfectly for the 4 outboard engines. But the center engine had a slightly different feedline geometry. The resonant frequency was different. Not by much, just enough. And the helium cavity that had been optimized for the outboard engines wasn't quite right for the center engine. Under the specific conditions of the Apollo 13 ascent, with the specific propellant load and the specific throttle profile, the center engine entered a pogo condition. The oscillations grew. The automatic shutdown system did exactly what it was designed to do. It shut down the engine before it destroyed itself or the vehicle. The mission continued on 4 engines. The trajectory was adjusted. The spacecraft reached orbit. And then, 56 hours later, oxygen tank number 2 exploded, and the pogo event became a footnote. But that footnote contains a lesson that matters more now than it did then. After Apollo 13, NASA investigated the pogo event. They refined the helium injection system for the center engine. The fix was implemented on Apollo 14 and all subsequent flights. No more pogo events occurred in the Apollo program. Problem solved, this time for real. And then the knowledge began to disappear. The engineers who solved pogo didn't write comprehensive textbooks about it. They wrote technical reports, filed in NASA archives, dense with mathematics and specific to Saturn V systems. The Rocketdyne team moved on to other projects. Some retired. The institutional knowledge of exactly how they had solved the problem, the intuition they had developed through hundreds of hours of test fires and analysis, existed primarily in their heads and in their working relationships. When the Saturn V program ended in 1973, the production lines were dismantled. The tooling was destroyed or scattered to museums, and the engineering teams dispersed. Some went to shuttle, some went to private industry, some left aerospace entirely. The detailed, practical, hands-on knowledge of pogo suppression went with them. The technical reports remained. But here's the thing about technical reports. They document what was done. They don't always capture why certain decisions were made, what alternatives were tried and failed, what intuitions guided the successful approach. That knowledge is tacit. It lives in the minds of engineers who have spent years working on a specific problem. And when those engineers leave, that knowledge leaves with them. Fast forward to 2016. SpaceX is flying Falcon 9 rockets at an increasing cadence. The Falcon 9 uses 9 Merlin engines on the first stage, fed from common propellant tanks. During some flights, telemetry showed unexpected oscillations in the first stage. Not severe enough to cause problems, but present. Engineers investigated. The characteristics were consistent with Pogo. SpaceX has some of the best aerospace engineers in the world. They have access to NASA's technical archives. They can read the Apollo-era reports on Pogo suppression. But reading a report is not the same as having solved the problem yourself. The Merlin engine is not the J2. The propellant is different. The feed system geometry is different. The resonant frequencies are different. The solution has to be developed again, from first principles, using the Apollo reports as a starting point, but not as a blueprint. SpaceX adapted Apollo-style damping approaches for their feed systems, but it takes months of analysis and testing, months spent addressing a problem that had been solved 50 years earlier. Not because the SpaceX engineers are less capable than the Apollo engineers, but because the specific, detailed, practical knowledge of how to solve Pogo for a particular rocket configuration had been lost. Now consider Starship. 33 Raptor engines on the Super Heavy booster, all fed from common propellant tanks. The potential for Pogo oscillations is enormous. The complexity of the feed system, with 33 engines instead of 5 or 9, creates resonant modes that have never been encountered before. SpaceX is working on Pogo suppression for Starship right now. They're using modern computational fluid dynamics, modern sensors, modern control systems. But the fundamental problem they're solving is the same problem that Rocketdyne engineers solved in 1968. This is the tragedy of lost institutional knowledge. Not that the problem is unsolvable. It was solved. It can be solved again. The tragedy is the waste. The time spent re-deriving solutions that once existed. The risk of making mistakes that were already made and corrected decades ago. The possibility that we might lose people or missions to problems we had already learned to prevent. And Pogo is just one example. The list of forgotten aerospace knowledge is long and disturbing. The metallurgy of the F1 engine, the specific welding techniques for the Saturn V propellant tanks, the thermal protection systems for Apollo Reentry. NASA has admitted publicly that they could not build a Saturn V today, even with the original blueprints, because too much of the manufacturing knowledge was never documented. It existed in the skills of the workers and the practices of the factories, and it's gone. This isn't unique to aerospace. The construction techniques for Roman concrete, which has lasted 2,000 years while modern concrete crumbles in decades, were lost for centuries and are only now being partially rediscovered. The methods for creating certain medieval pigments are gone. The specific alloys used in Damascus steel are still debated. Humanity has a long history of forgetting how to do things it once did routinely. But in aerospace, the consequences are measured in lives and in the future of spaceflight. When Apollo 13's center engine shut down, the crew survived because the rocket had enough margin to reach orbit on 4 engines. If the Pogo oscillations had been more severe, if they had affected multiple engines, if the structural loads had exceeded design limits, 3 astronauts would have died. And the reason they were at risk was that a problem which had been solved was not solved completely enough, not documented thoroughly enough, not transmitted to the next generation of engineers effectively enough. The Apollo 13 accident investigation focused rightly on the oxygen tank explosion. That was the immediate threat to the crew. But the Pogo event was a warning sign. It indicated that even with the best engineering in the world, even with unlimited resources and national priority, knowledge can slip away. Solutions can become incomplete. Understanding can fade. Today, we're in a new era of space exploration. Multiple companies are building heavy-lift rockets. NASA is developing the Space Launch System. China is expanding its space program. India is planning crewed missions. And every single one of these efforts is encountering problems that were solved 50 or 60 years ago. Not because the solutions were wrong, but because the solutions were not preserved in a form that could be effectively transmitted across generations and across organizations. The technical reports exist. The papers are in the archives. But the reports don't capture everything. They don't capture the failed approaches, the blind alleys, the intuitions that guided experienced engineers away from solutions that looked promising but wouldn't work. They don't capture the tacit knowledge, the feel for the problem that comes from years of hands-on work. And without that knowledge, each new generation has to learn some of the same lessons over again. There's a deeper problem here. The engineers who solved Pogo for Saturn V are mostly gone now. They've retired or passed away. The institutional memory at NASA has been disrupted by budget cuts, program cancellations, and the decades-long gap in heavy-lift vehicle development between Saturn V and SLS. The continuity of knowledge has been broken, and we're seeing the consequences. The SLS program has encountered Pogo concerns. The engineers working on SLS have had to go back to the Apollo-era reports and rederive solutions for a vehicle with different engines, different propellants, different geometry. SpaceX is doing the same for Starship. Blue Origin will face the same issues with New Glenn. Every new large rocket will encounter Pogo, and every development team will spend time and money solving a problem that has been solved before. This is inefficient, it's wasteful, and it's dangerous. Because each time we resolve the problem, there's a risk we'll miss something. A risk we'll make a mistake that was already made and corrected in the 1960s. On a risk that the solution won't be quite right, and we'll find out during a crewed flight. The solution isn't simple. You can't just preserve technical reports and expect that to be enough. You need to preserve the people, or at least their knowledge. You need continuous programs that maintain institutional expertise across generations. You need apprenticeship models where experienced engineers work directly with newer engineers, transmitting not just facts but intuition and judgment. You need organizations that value and retain deep technical knowledge, not just management skills. NASA understood this once. The Apollo program had a culture of technical excellence where engineers stayed on projects for years, building deep expertise. But that culture was disrupted by the end of Apollo, by budget cuts, by the shift to shuttle, by decades of changing priorities and canceled programs. The continuity was broken, and now we're paying the price. The most dangerous problem in rocketry isn't explosion. Explosions are dramatic, but they're also obvious. You see them happen, you investigate, you fix the immediate cause. The most dangerous problem is forgetting. It's silent. It's gradual. It doesn't announce itself with fire and smoke. It just means that one day you encounter a problem you should know how to solve, and you don't. And people die because of knowledge that once existed and was lost. Apollo 13's center engine shutdown was a warning. It told us that even solved problems can come back, that solutions need to be maintained, transmitted, preserved. That institutional knowledge is fragile. We didn't listen well enough. We're relearning the same lessons now, 50 years later, as we try to return to the moon and push on to Mars. The question is whether we'll learn this time, whether we'll build the systems and the culture to preserve what we discover, whether we'll value the deep technical knowledge that prevents disasters as much as we value the dramatic responses after disasters occur, whether we'll remember that the hardest problems aren't always the ones that explode in your face. Sometimes they're the ones that quietly slip away, waiting to surprise the next generation that has to solve them all over again. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching. The standard narrative tells us that Apollo 18, 19, and 20 were canceled due to budget cuts. That the hardware sat in warehouses and eventually found its way to museums. That America simply lost interest in the moon and walked away from billions of dollars in flight-ready equipment. This story is not entirely false, but it is not entirely true either. 3 Saturn V rockets were built, tested, and certified for flight after Apollo 17. SA-514, SA-515, and SA-515 stood ready in their assembly buildings. Command modules were wired and pressure tested. Lunar modules were fueled and waiting. The missions had landing sites selected, crew assignments drafted, and science packages manifested. Then, in September 1970, NASA announced the cancellations. The official reason: budgetary constraints and shifting priorities toward the Space Shuttle program. What the official announcements did not mention was where those priorities actually shifted. The hardware did not simply gather dust. Critical components were harvested, repurposed, and integrated into programs that would never appear in NASA press releases. The optical systems, guidance computers, and thermal protection technologies developed for lunar missions found new homes in the classified world of military space operations. To understand how this happened, we need to examine what Apollo actually was beneath its civilian exterior. If you're interested in the real story behind space programs, the technology that actually flew, the decisions that never made the press releases, and how space became a strategic domain, subscribe to Space Cluster. We focus on what was built, why it mattered, and where it really led. Now, back to the story. From the beginning, Apollo existed in a dual-use environment. The National Aeronautics and Space Act of 1958 established NASA as a civilian agency, but it explicitly required cooperation with the Department of Defense on matters of national security. This was not a footnote. It was fundamental architecture. Every Apollo mission plan was reviewed by DoD representatives. Every technical capability was assessed for potential military application. Every orbital pass over Soviet territory was tracked by both NASA and the National Reconnaissance Office. The Soviets understood this immediately. Soviet military doctrine assumed that any American spacecraft capable of reaching the moon was also capable of deploying weapons, conducting reconnaissance, or serving as an orbital strike platform. This was not paranoia. It was rational analysis based on capability, not intent. The same rocket that could send 3 men to lunar orbit could also place a multi-ton military payload into any orbit around Earth. The same navigation systems that could guide a spacecraft to a precise landing on the moon could guide a warhead to a precise target on Earth. Soviet responses reflected this assessment. The Almaz military space station program, initiated in 1964, was explicitly designed as a manned reconnaissance platform with defensive capabilities. The station carried a 23mm cannon, tested successfully in orbit in 1975. The Polyus weapons platform, launched in 1987, was designed to destroy American satellites and potentially ground targets. These were not reactions to American aggression. They were reactions to American capability. And that capability was built, tested, and proven through Apollo. The technical evidence of military involvement is not speculative. It exists in declassified documents, manifests, and engineering specifications. Starting with Apollo 14, every lunar mission carried Department of Defense experiments. These were not informal add-ons. They were formally manifested payloads with dedicated power, telemetry, and crew time allocations. Apollo 14 carried cosmic ray detectors that were simultaneously studying radiation environments and gathering data on radiation weapon effects. Apollo 15 deployed laser retroreflectors officially described as tools for measuring Earth-Moon distance. They were also precision targeting calibration systems. The camera systems provide the clearest lineage from lunar exploration to orbital reconnaissance. The Apollo Lunar Module Descent Camera used an 80mm lens system capable of 1-meter resolution from 100 kilometers altitude. This was cutting-edge optical engineering in 1969. The same engineering team at Perkin-Elmer that designed these systems was simultaneously developing the KH-9 Hexagon reconnaissance satellite, which began operations in 1971. The KH-11 Kennan satellite, first launched in 1976, used a Hubble-class mirror built by the same contractors, using techniques refined during Apollo. This was not coincidence. It was deliberate technology transfer under overlapping classified contracts. The optical engineers working on lunar photography were cleared for compartmented programs. The thermal coatings protecting Apollo capsules during re-entry were tested in parallel with thermal protection systems for re-entry vehicles carrying reconnaissance film. The guidance computers that navigated to the moon were developed alongside guidance systems for strategic missiles. Apollo was not a cover for military programs. It was a parallel development environment where civilian achievements provided cover for classified advances. When Apollo 18, 19, and 20 were canceled, the hardware did not simply disappear into storage. SA-514 and SA-515, the Saturn V rockets built for these missions, were officially retired to museum display. SA-514 is suspended horizontally at the Johnson Space Center. SA-515 is displayed at the Kennedy Space Center. But the upper stage technology, the J-2 engines, and the guidance systems were documented, analyzed, and fed directly into subsequent heavy-lift programs. The modifications made to launch the KH-9 Hexagon satellites, which weighed over 30,000 pounds, incorporated lessons learned from Saturn V upper stage design. The Apollo Block II command modules built for the canceled missions had a feature rarely discussed in public documentation: classified equipment bays. These were not small compartments for personal items. They were substantial pressurized volumes with dedicated power, cooling, and data recording systems. The specifications for these bays appear in heavily redacted technical documents released decades later. What was intended to go into these spaces? The official answer is scientific instruments. The actual answer is more complex. The Manned Orbiting Laboratory Program, canceled in June 1969, was designed to place Air Force astronauts in orbit for 30-day reconnaissance missions. The crew capsule for MOL was a modified Gemini spacecraft. When MOL was canceled, its mission requirements did not disappear. They migrated. The Apollo equipment bays had dimensions and capabilities that closely matched MOL payload requirements. The thermal control systems, the optical quality windows, the vibration isolation mounts, all of these existed in Apollo hardware and could be repurposed for classified payloads in Earth orbit. There is a document, declassified in 1998, that makes this explicit. The 1970 NASA DoD Memorandum of Understanding formalized payload sharing between civilian and military space programs. It established procedures for manifesting classified experiments on NASA missions, protocols for crew security clearances, and guidelines for data handling. This was not a new arrangement. It was formalization of practices that had existed since Gemini. But the timing is significant. The memorandum was signed 7 months after Apollo 11, as Apollo missions were transitioning from proof of concept to operational capability. The public narrative describes the end of Apollo as a failure of imagination, a surrender to budgetary pressure, a loss of national will. This narrative is emotionally satisfying but factually incomplete. The actual decision-making process was more complex. The Nixon administration conducted a comprehensive review of space priorities in 1969 and 1970. The Space Task Group, chaired by Vice President Spiro Agnew, presented 3 options: an ambitious program including lunar bases and Mars missions, a moderate program focused on Earth orbit operations, and a minimal program maintaining basic capabilities. Nixon chose none of these options as presented. Instead, his administration restructured space priorities around dual-use capabilities. The Space Shuttle was approved not because it was the best vehicle for scientific exploration, but because it could serve both civilian and military missions. The shuttle payload bay dimensions were driven by National Reconnaissance Office requirements for satellite deployment. The cross-range capability, which added enormous complexity and weight, was required for single-orbit military missions launching from Vandenberg Air Force Base. This restructuring meant that Apollo-class capabilities did not disappear. They were redistributed. The heavy lift capacity of Saturn V was replaced by Titan IV rockets launching classified payloads. The precision landing capability of the Apollo command module informed the development of maneuverable re-entry vehicles. The life support systems that kept astronauts alive for 2 weeks in lunar orbit were studied and improved for long-duration military space stations that were designed, but never publicly acknowledged. The optical reconnaissance lineage is the most direct and documentable connection. The KH-11 Kennen satellite, first launched in 1976, represented a revolution in reconnaissance. Unlike earlier systems that returned film canisters to Earth, KH-11 transmitted digital imagery in near real time. The primary mirror was 2.4 meters in diameter, identical to the Hubble Space Telescope launched 14 years later. This was not coincidence. Both were built by Perkin-Elmer using the same facilities and, in some cases, the same tooling developed during Apollo-era optical programs. The performance specifications of KH-11 remain partially classified, but declassified imagery and technical assessments indicate sub-meter resolution from orbits above 250 kilometers. This means the satellite could distinguish objects the size of a baseball home plate from the edge of space. The optical coatings, the mirror polishing techniques, the vibration isolation systems, all of these traced lineage to Apollo-era development programs. The engineers who designed cameras for the moon designed cameras that watched Soviet missile fields. This technology did not remain static. The KH-11 program continued through multiple generations, each improving on the last. The final KH-11 variant, launched in the 2010s, uses adaptive optics, synthetic aperture radar integration, and signal processing capabilities that would have been incomprehensible in 1976. But the fundamental architecture, the optical design philosophy, the thermal management approach, these all descend from decisions made during Apollo. The modern legacy is not hidden in museums. It is overhead right now. The satellites photographing Russian troop movements in Ukraine, tracking Chinese naval deployments in the South China Sea, and monitoring Iranian nuclear facilities are the direct descendants of Apollo-era reconnaissance technology. The National Reconnaissance Office operates a constellation of imaging satellites that collectively represent the most sophisticated surveillance network ever created. The fact that this capability exists is public. The details remain classified, but the engineering lineage is clear to anyone who examines the technical literature. The X-37B orbital test vehicle represents another branch of this lineage. This reusable military spaceplane, operated by the United States Space Force, has conducted multiple missions lasting over 900 days in orbit. Its payload is classified. Its mission objectives are classified. Even its orbital parameters are sometimes classified. But its automated landing system, its thermal protection approach, and its guidance algorithms all trace ancestry to Apollo-era development. The X-37B is what Apollo hardware becomes when it evolves in the classified world for 50 years. China has studied this lineage carefully. The Chinese lunar exploration program has examined Apollo landing sites with orbital imaging. Chinese technical literature explicitly analyzes Apollo systems architecture. This is not academic interest. It is operational intelligence gathering. Understanding how America integrated military and civilian space capabilities in the 1960s and 1970s informs Chinese strategic planning today. The dual-use nature of space technology has not changed. If anything, it has intensified. The question is not whether Apollo hardware was repurposed for military applications. The declassified record makes clear that it was. The question is how much of Apollo was always intended for dual use, and how much of the civilian program served as cover for military development. The answer is probably both. NASA engineers genuinely believed they were exploring the moon for peaceful purposes. DoD planners genuinely believed they were leveraging civilian programs for national security. These perspectives were not contradictory. They were complementary. There is a deeper question that remains largely unexamined. If Apollo-derived technology provided such significant military advantages, why was the program canceled at all? Why not continue lunar missions while simultaneously developing reconnaissance satellites? The answer involves budgetary constraints, but it also involves strategic calculation. Continuing Apollo meant continuing a highly visible program that invited Soviet scrutiny and response. Transitioning those capabilities into classified programs reduced visibility while maintaining operational advantage. This calculation was not unique to the United States. The Soviet Union conducted its own dual-use space programs, often with even less distinction between civilian and military applications. The Salyut space station program included both civilian scientific stations and military Almaz reconnaissance stations using nearly identical hardware. The Energia heavy-lift rocket was developed primarily for military payloads, including the Polyus weapons platform, but was publicly presented as a civilian launch vehicle. Both superpowers understood that space technology was inherently dual-use. The tragedy, if there is one, is not that Apollo ended. It is that the public understanding of what Apollo was remains incomplete. The standard narrative presents a clear division: civilian space exploration for peaceful purposes, separate from military space operations. This division never existed. Apollo was always a hybrid program, serving multiple purposes simultaneously. Recognizing this does not diminish the achievement of landing humans on the moon. It contextualizes that achievement within the strategic environment that made it possible. The hardware built for Apollo 18, 19, and 20 represents a specific moment when this dual-use nature became explicit. 3 complete moon missions, ready to fly, were canceled, not because the capability was no longer needed, but because the capability could be better utilized elsewhere. The rockets, capsules, and systems built for lunar exploration were too valuable to waste on additional moon landings when they could advance reconnaissance, communications, and strategic capabilities. This is not speculation. It is documented in budget documents, technical reports, and strategic assessments declassified over the past 3 decades. The National Reconnaissance Office budget increased substantially in the early 1970s, precisely as Apollo was winding down. The number of reconnaissance satellite launches increased. The sophistication of imaging systems improved dramatically. This was not coincidence. It was resource reallocation from one national priority to another. The rockets in the museums are not monuments to failure. They are monuments to misdirection. They represent a capability that was built, proven, and then deliberately set aside in favor of capabilities that would not be photographed, celebrated, or publicly acknowledged. SA-514 and SA-515 could have sent astronauts back to the moon. Instead, their technology sent cameras over Moscow, guidance systems into strategic missiles, and thermal protection systems onto re-entry vehicles carrying classified payloads. The real Apollo program never ended. It just stopped being called Apollo. The engineers moved to different programs. The contractors shifted to different projects. The technology evolved in directions that would not be publicly disclosed for decades. When we look at the Apollo hardware in museums, we are seeing only half the story. The other half is overhead right now. In orbits we can calculate, but payloads we can only infer. This is the shadow history of Apollo. Not a story of dreams abandoned, but of capabilities redirected. Not a failure of will, but a strategic choice to prioritize operational advantage over public spectacle. The hardware was too valuable to waste. The technology was too advanced to abandon. So it went dark, and it stayed dark, and it evolved into systems that remain classified today. When China lands astronauts on the moon in the coming years, they will be following a path that America walked more than half a century ago. But they will also be following a strategic playbook that America wrote. Develop capabilities under civilian cover, harvest technology for military applications, and maintain ambiguity about ultimate intentions. The Apollo template was not just about reaching the moon. It was about building dual-use capabilities that could serve multiple strategic purposes simultaneously. The canceled missions were not lost opportunities. They were calculated sacrifices. The hardware was not abandoned. It was repurposed. And the program did not end. It transformed into something that could not be photographed for the evening news, something that would not inspire children to become astronauts, something that would remain hidden until decades after the fact, if ever. That is the real story of Apollo 18, 19, and 20. Not missions that never flew, but capabilities that never stopped flying. The moon was always secondary. The reconnaissance, the strategic advantage, the technological superiority, that was the real mission. And that mission continues. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.
He was the man who beat America to space. He launched the first satellite. He put the first human into orbit. But for decades, the world didn't even know his name. To the CIA, he was a ghost. To the Soviet Union, he was a heavily guarded state secret. But the darkest secret of all wasn't his identity. It was what his own country did to him. This is the hidden history of the genius who built the space age, and how a single, brutal beating in a Siberian prison camp secretly changed the course of human history. Moscow, January 14th, 1966. It's cold outside, but inside the hospital everything is white and warm and quiet. A man is lying on an operating table. He's 59 years old. His face is tired. The anesthesiologist picks up the intubation tube. This is the tube they slide down a patient's throat before surgery. It keeps the airway open. It keeps people alive. Standard procedure. Takes about 30 seconds. He leans forward, and then he stops. Something is wrong. The man's jaw won't open. Not fully. Not enough. The doctor tries again, gently, then less gently. He looks closer. There's an old fracture there. You can see it in the bone structure. The jaw was broken once badly broken, and it healed wrong. The joint fused at the wrong angle. It left a gap too small for the tube to pass through. The doctor calls for the surgeon. The surgeon examines the jaw. He looks at the patient's face. He makes a decision. They'll try a different approach, a more dangerous one. They proceed. The surgery takes hours. Complications pile up, one after another like dominoes falling in slow motion. Sergei Korolev does not survive, and in that moment a wound from 1938 finished what it started, a beating, in a prison camp, 28 years earlier, reached forward through time and killed the man who launched humanity into space. To understand what was lost, you have to understand what existed before it was almost destroyed. Sergei Pavlovich Korolev was born in 1907 in Ukraine. His parents split up when he was 3. He was raised mostly by his grandparents. He wasn't a sad kid, he was a curious one. The kind of kid who takes things apart to see how they work and then builds something better out of the pieces. By the time he was a teenager, he was obsessed with flight. Not just airplanes. Rockets. This was the 1920s. Most people thought rockets were science fiction, Jules Verne stuff, fairy tales for engineers. Korolev didn't care what most people thought. He studied engineering in Moscow. He was loud. He was difficult. He argued with his professors when he thought they were wrong. And he was usually right. He had a gift that was almost annoying to be around, because he couldn't turn it off. In 1931, he helped found GERD, the Group for the Study of Reactive Motion. This was a small team of Soviet engineers who believed, against all reasonable evidence, that rockets could one day carry human beings beyond Earth. They were broke. Their workshop was a basement. They called it the cave. They had almost no equipment and almost no support. They built rockets anyway. In 1933, their rocket called GIRD-09 flew 400 meters into the air. It wasn't much, but it was real. It left the ground. It came back down. And Korolev stood there watching it and thought, this is just the beginning. He was healthy then, strong. He talked fast when he got excited. His jaw moved easily when he laughed, and he laughed a lot in those early years. Remember that, because in a few years the state is going to try to erase this man completely. In 1937, the Soviet Union went insane. That's not an exaggeration. That's just what happened. Joseph Stalin became convinced that enemies were everywhere. Spies, saboteurs, counter-revolutionaries hiding inside the government, inside the military, inside every factory and university and research lab in the country. He started arresting people. Not just actual enemies, not just criminals. He arrested engineers, scientists, artists, soldiers, loyal Communist Party members who had done nothing wrong. He arrested them by the millions, and people who were scared of being arrested themselves. They looked for someone to blame, someone to denounce. If you pointed a finger at someone else, maybe the finger wouldn't point at you. In June 1938, someone pointed a finger at Korolev. The charges were fabricated. Sabotage. Counter-revolutionary activity. He had supposedly been working against the Soviet state. the man who spent his entire adult life building rockets for the Soviet state. It didn't matter. The charges didn't need to be true. They just needed to exist. Korolev was arrested. He was interrogated, beaten, pressured to confess to crimes he didn't commit. He refused. He was tried anyway, found guilty anyway, sentenced to 8 years of hard labour. They sent him to Kolyma. Kolyma is a region in the far northeast of Russia, close to the Arctic Circle. In winter, temperatures drop to 60 below zero. The ground is frozen solid. The sky stays dark for months. The Gulag sent prisoners there to mine gold. The death rates were catastrophic. Men died from cold, from starvation, from disease, from exhaustion, from violence. Korolev arrived in 1939. He was 32 years old. He weighed about 70 kilograms when he left Moscow. He would weigh much less before he left Kolyma. At some point, the exact date is unclear, the guards beat him. They broke his jaw, knocked out several of his teeth. No doctor set the bone properly. There was no proper medical care in Kolyma. The jaw healed on its own, slowly and badly. The bone fused at a slight wrong angle. The joint never moved quite right again. He also developed scurvy, vitamin C deficiency so severe it almost cost him his eyesight. His gums bled, his joints ached. He was starving. Here is a man who had been, 3 years earlier, building rockets and dreaming about space. And now he was digging frozen ground in the dark with a broken jaw, going slowly blind. Then something unexpected happened. A Soviet aviation pioneer named Sergei Tupolev, who was himself a prisoner, intervened. He put in a request. He said he needed engineers, skilled ones, the kind you couldn't replace. The Soviet bureaucracy, which had just tried to murder Korolev, now needed him to be useful. He was transferred, not to freedom, to a Sharashka. A Sharashka was a secret research facility inside the Gulag system, a prison for scientists. The prisoners wore their camp uniforms. They were watched. They couldn't leave, but they had desks. They had drawing boards. They had tools. They worked on Soviet military technology in chains, literally and figuratively, in chains. Korolev sat down at a desk in a Sharashka and got back to work. Because what else was he going to do? He spoke differently now. The jaw made certain sounds harder. Some people who knew him before and after the Gulag noticed it immediately. His voice had changed. There was something stiff in the way he moved his mouth. The body remembers what the state wants to forget. Stalin died in 1953. The Soviet Union exhaled. The new leadership, eventually led by Nikita Khrushchev, began what they called the thaw. Political prisoners were reviewed. Sentences were reconsidered. In 1944, Korolev had already been officially released, though he remained under surveillance and restriction. In 1957, his conviction was formally vacated, rehabilitated. That was the word they used. No apology, no acknowledgement of what had been done to him, no compensation for the years stolen or the body damaged or the career interrupted. Just, your paperwork has been corrected. You may return to being useful now. Korolev returned to being useful. He threw himself into the R-7 rocket program with the same intensity he'd had in the 1930s. Maybe more. He was older now. He knew time wasn't unlimited. He drove his team hard. He was demanding, sometimes impossible. He had no patience for excuses. He had a goal. He wanted to put something in orbit. Something that circled the Earth. Something that proved it could be done. The Americans were working on the same goal. The Cold War was turning into a space race. Whichever side got there first would have bragging rights, and something more than that. Proof. Proof that their system, their ideology, their way of organizing society was superior. Korolev couldn't have cared less about the ideology. He cared about the rockets. On October 4th, 1957, the R-7 rocket lifted off from a launch site in Kazakhstan. On its tip sat a small metal sphere, about the size of a beach ball. It had 4 antennas sticking out of it like legs on an insect. It was called Sputnik. It reached orbit. It circled the Earth every 96 minutes, beeping a radio signal anyone could hear. Korolev stood in the control room. He listened to the signal come back from space, and he cried. 20 years of work, a broken jaw, a gulag, scurvy, near blindness, chains, and the rocket still worked. The next morning, The world woke up to the news. Khrushchev celebrated the victory. Soviet newspapers ran the story on the front page. The Americans were shocked into silence. And Sergei Korolev? His name was classified. He was called only the chief designer. No photograph, no public identification. The man who had just changed the course of human history was not permitted to say he had done it. He went home. He ate dinner, slowly, as he always did now. The jaw made eating uncomfortable. It had since 1938. He had just launched humanity's first satellite into orbit, and then he went home to a jaw that still hurt when he chewed. Sputnik was just the opening move. Korolev wanted more. He always wanted more. Within weeks of the first satellite, he was pushing for the next thing, an animal in orbit, then a human. The Americans were pushing too. Both sides were spending enormous amounts of money and talent trying to be first. Korolev managed all of it from a position that should have been impossible. He was running the most important engineering program in Soviet history. He had no public identity. His name was secret. If he travelled abroad, he did so under a false name. He was also sick. His heart was not healthy. His kidneys gave him trouble. Decades of accumulated damage from Kolyma had never fully healed. His immune system had been compromised by starvation and cold in ways that doctors didn't fully understand. He pushed through it. He always pushed through. By 1960, the Soviets had launched dogs into orbit and brought them back alive. The next step was a human. The question was who? Korolev was personally involved in selecting the cosmonauts. He met with each of them. He watched them in training. He had opinions about who was ready. He chose Yuri Gagarin. Gagarin was 27 years old. He was from a small village. His father was a carpenter. He was charming and warm and genuine, the kind of person who made everyone around him feel at ease. He had also, it turned out, scored highest on nearly every evaluation they ran. Korolev liked him immediately. On the morning of April 12, 1961, Gagarin was helped into his spacesuit at a launch site in Kazakhstan. He rode a bus out to the rocket. He climbed up to the capsule. He strapped in. Before the hatch sealed, Korolev spoke to him over the radio. He told him to be careful. He told him they were proud of him. He told him, and this is real, this is documented. We'll see you soon. A father sending a son somewhere he cannot follow. The rocket fired. Gagarin left Earth. He orbited the planet once, in 108 minutes. He looked down through the window and later said the Earth was beautiful. Blue, surrounded by black. Korolev stood in the control room in Kazakhstan the whole time. He didn't move. He barely breathed. Gagarin came home safely. His capsule landed in a field in Russia. A farmer and her granddaughter watched him climb out of his spacesuit. He asked them for a phone. The celebration started immediately. Gagarin was flown to Moscow. He was driven through the streets in an open car. Millions of people lined the route. Khrushchev stood next to him in Red Square. The whole world was watching. Yuri Gagarin became the most famous human being alive, and Korolev went back to the control room. He watched the parade on a small television. His name was still classified. His face was still unknown. The engineers around him were celebrating, and he celebrated with them. But he could not call his mother and tell her what he had done. She would have had no idea. The man who sent the first human into space could not tell his own mother that he had done it. There is a photograph from around this time, one of the rare ones where Korolev appears. If you look carefully at his jaw, at the line of his face, you can see it. The left side sits slightly differently than the right. The healed fracture altered the structure of his face. History was written on his bones. After Gagarin, the pace only accelerated. The Americans were not going to give up. NASA was building bigger rockets and planning bigger missions. Khrushchev wanted the Soviets to stay ahead. He pressured Korolev constantly. More firsts, more milestones, more propaganda victories. The first woman in space, Korolev, the first spacewalk. Korolev. Every Soviet achievement in space in this era traces back to one desk, one brain, one broken body driving itself beyond what it should have been capable of. He was also fighting battles inside the Soviet system itself. There were other rocket designers, other engineers who wanted resources, funding, glory. There were military officials who had different priorities. There was politics at every level. Korolev had to fight for his program constantly, using a combination of results and personality that no one else could quite replicate. He was not always easy to work with. He was demanding. He had a temper. He worked 18-hour days and expected people around him to keep up. But his team was loyal to him in a way that went beyond professional respect. They could see what he had survived. They knew what it cost. By the mid-1960s, the race to the moon was the only thing that mattered. And Korolev's body was failing. His heart was weak. His blood pressure was dangerously high. Doctors told him to slow down. He ignored them. He told them to give him something for the pain and let him work. In late 1965, he started experiencing abdominal discomfort. It got worse. By early January 1966, there was bleeding. The doctors found polyps in his intestine. They recommended surgery. It was described as minor, routine, the kind of procedure a man in his 50s went through and came home from. Korolev agreed. He was admitted to the hospital on January 14, 1966. He had been building toward the moon. He had programs running. He had rockets being designed. He had a desk covered in work. He walked into that hospital fully expecting to come back. You know what's waiting for him in that operating room. You've known since the first minute of this video. Watch anyway. The operating room is white and still. The anesthesiologist prepares the intubation tube. He moves toward Korolev's face, and the jaw won't open. Not enough. The old fracture, the one from Kolyma, from 1938, from a guard who hit a prisoner who happened to be the most important engineer in the world, that fracture healed wrong. The bone fused at a slight angle. The joint lost some of its range of motion. A small thing, really. A few millimeters. But a few millimeters is everything when you're trying to pass a tube into a man's airway. The surgeon is called in. He examines the jaw. He understands the situation. They cannot do this the standard way. They will have to do it differently. An incision into the airway directly. More dangerous, more complex. The surgery begins. What was supposed to take a few hours takes much longer. Complications develop. The team works. They fight. Sergei Korolev, 59 years old, the man who built the Soviet space program with his bare hands and his brilliant broken mind, dies on the operating table. The date is January 14th, 1966, the same day he was admitted. After his death, the Soviet government does something remarkable. They reveal his name. The obituary appears in Pravda. It is the first time most Soviet citizens have ever seen the words Sergei Pavlovich Korolev in a newspaper. The first time they learn who the chief designer was. The first time they know the name of the man behind Sputnik, behind Gagarin, behind every triumph they had been celebrating for a decade. They found out who he was the day after he died. Yuri Gagarin served as a pallbearer at his funeral. The man Korolev sent to space carried Korolev's ashes on his shoulders. His ashes were placed in the Kremlin wall, one of the most honoured burial sites in the Soviet Union. Reserved for heroes. The system that broke his jaw buried him as a hero. Let's add this up. In 1938, the Soviet government arrested Sergei Korolev on false charges, sent him to one of the most lethal prison camps on Earth, let prisoners beat him until his jaw shattered, watched him develop scurvy and go nearly blind, worked him too, near death. Then they decided they needed him. So they put him at a desk and told him to build missiles. He did. They released him, sort of. They rehabilitated him, sort of. They never said they were sorry. He built Sputnik, the first satellite in history. They classified his name. He built the rocket that carried Gagarin, the first human in space. They classified his name. He built the program that put the first woman in space, the first spacewalk, the first multi-person crew. They classified his name. He did all of this with a jaw that didn't work right, a heart that was wearing out, kidneys that never fully recovered from what Kolyma did to them. He did all of this knowing, on some level, what the state was, what it had done to him, what it was capable of, and he built their rockets anyway. Because the rockets were real. Because space was real. Because no matter what the system around him did, the laws of physics stayed the same. A rocket didn't care who built it. An orbit didn't care what your name was. And when the surgery came, when there was finally a simple, fixable medical problem, the jaw said no. The jaw that broke in 1938. The jaw that healed wrong because there was no medical care in Kolyma. The jaw that a guard fractured on a prisoner who hadn't done anything wrong. That jaw, 28 years later, closed off the airway and killed him. Sputnik, Gagarin, Tereshkova, the R-7. All of it built by a man whose body was a crime scene. The Soviet Union did not build the space age. Sergei Korolev built
3 minutes and 7 seconds before liftoff, the entire rhythm of the Saturn V launch operation changes. Up to this instant, the countdown has been an intricate conversation between thousands of sensors, hundreds of controllers, and the enormous 3-stage launch vehicle standing on Pad 39A. But at T-307, a moment almost invisible to the casual observer, human control steps aside. The terminal countdown sequencer takes command. This sequencer is not a modern computer. It has no microprocessor, no magnetic core memory, and no software in the sense we use the word today. Instead, it is a relay logic machine. Banks of precision electromechanical relays wired to execute the last 100 or so critical operations strictly by timing, sequencing, and confirmation logic. What makes it astonishing is not its complexity, but its reliability. It must execute perfectly every single time. Because in these final minutes, the Saturn V is entering a configuration so delicate, so tightly constrained, that even a pause of a few seconds could cause physical damage to the vehicle or a dangerous overpressurization of its tanks. If you're interested in the real story behind space programs, the technology that actually flew, the decisions that never made the press releases, and how space became a strategic domain, subscribe to Space Cluster. We focus on what was built, why it mattered, and where it really led. Now, back to the story. The moment the sequencer awakens is triggered by a human go from the firing room. Launch controllers issue a discrete firing command, not a button held down, but a signal verified by the ground computer before releasing the terminal countdown sequencer. As the digital countdown clock rolls through 3 minutes and 7 seconds, the ground control system confirms the firing command has been issued. If it has, the sequencer is released. If it has not, the Saturn V will not launch. But once that logic gate is satisfied, humans no longer have any control. You cannot pause the countdown. The sequencer either completes its timeline, or a cutoff forces a recycle that drives the countdown back to a predefined hold point around T-22 minutes, with the required dwell there before resuming. Because by this point, super-cold cryogenic propellants are already conditioning the structure from the inside, hydraulic and pneumatic systems are shifting into flight mode, and internal batteries are beginning to assume more and more load. This is not just a procedural convenience. It is a necessity dictated by physics. The rocket must go, or it must stop entirely. In 13 Saturn V launches, the terminal countdown sequencer completed its job perfectly every time, with one near exception. On Apollo-12, relay chatter caused a failure in the S-4B third-stage LOX pressurization sequence. An operator had to manually intervene, one of the rarest events in post-sequencer operations. The sequencer was that reliable. And when it wasn't, people were ready. Meanwhile, inside the spacecraft nearly 400 feet above the pad, the crew is preparing for the transition from pre-launch to ascent. The command module's computer is running Program 02, of the platform alignment routine that maintains the inertial platform orientation with extraordinary accuracy. The platform is floated in a bath of fluorocarbon fluid, often referred to as Freon, suspended on gimbals with gyroscopes and accelerometers, forming the heart of the guidance system. It is the only reference the launch vehicle needs once it leaves the pad. Around 4 minutes before launch, the astronauts prepare a manual failsafe. They key in a sequence that will allow them to tell their computer that liftoff has happened should the automatic liftoff signal from the instrument unit fail to arrive. When the Saturn V actually leaves the pad, the launch vehicle digital computer senses the umbilical disconnect and sends a signal to the spacecraft. The crew has practiced what to do if it fails. But in the history of the Saturn V, it never once failed. The crew does not press the enter key. They only arm the sequence. If the liftoff discrete never arrives, pressing enter would force the computer to switch to its ascent monitoring program. But if the discrete does arrive, as it always did, that single key press remains unused. a silent backup to a system that has been engineered to the limits of reliability. With the terminal countdown sequencer now running, a kind of mechanical choreography begins. Around T-minus 2 minutes and 30 seconds, helium systems begin pressurizing the propellant tanks across all three stages. The second stage LOX tank starts building pressure around T-minus 307, and its liquid hydrogen tank follows around T-minus 137. This helium plumbing is one of the most critical and least discussed systems on the Saturn V. A boil-off across stages must be controlled to less than 1% variance. Physics demanded perfect flow, or the sequencer would issue a cutoff. Pressurization valves throughout the stages shift from ground vent positions to launch positions. Up until this moment, the liquid oxygen tanks in all three stages have been venting to maintain temperature control. These tanks contain hundreds of thousands of liters of cryogenic oxidizer at temperatures low enough to make steel brittle and to freeze any atmospheric moisture into thick frost. As soon as the vent valves begin closing, the tanks begin building pressure, and that pressure must stabilize within tight limits, not too low, not too high, before ignition. The second stage in particular is tightly constrained. Its liquid oxygen tank must be pressurized within narrow limits to maintain structural rigidity and proper feed conditions while limiting boil-off. The terminal countdown sequencer checks multiple pressure sensors so quickly that the human eye cannot follow the logic on its diagnostic panels. In milliseconds, it determines whether stages 1, 2, and 3 are all reaching the required flight pressures at exactly the right pace. If any tank lags or surges, the sequencer issues a cutoff. There is simply no tolerance here. Throughout the vehicle, hydraulic systems transition from ground-supplied fluid to internal supply. In the first stage, the F1 engines rely on high-pressure hydraulic systems to gimbal the 4 outboard engine bells. Until moments before ignition, the used hydraulic fluid has been routed back to the ground through swing arm plumbing. But as the sequencer moves toward engine start, those fluid paths close. The engines now feed hydraulic fluid into their own turbopumps, preparing the gimbal actuators for the violent steering forces of ascent. Inside the command module, more transitions occur. The spacecraft has been running on full internal power since around T-minus 11 minutes, when the power transfer test confirmed all systems could operate on battery alone. At around 1 minute before liftoff, pad communications are disconnected. The crew can still hear mission control in Houston, but not the technicians and ground personnel who have now evacuated the entire launch complex. They are alone atop the most powerful machine ever built. 50 seconds before launch, the Saturn V confirms one of the most critical transitions of the countdown. The launch vehicle stages switch to internal electrical power. Each stage carries its own set of zinc-silver oxide batteries. The first stage carries multiple batteries for control and instrumentation. The second stage has 4. The third stage uses several batteries grouped into multiple buses, and the instrument unit carries 4 batteries of roughly 70 kilograms each. These batteries were installed less than 2 days earlier, fully charged and tested repeatedly. Now they come online. This transition is not merely a redundancy test. It is a requirement for ignition. Once the rocket begins its ascent, it can no longer rely on ground power. Thousands of amps surge through the internal buses as the rocket's electrical systems shift to flight configuration. Around 1 minute before launch, the crew starts the onboard data recorder. The tape inside begins capturing sensor data and voice recordings. This is a spacecraft black box, and for good reason. During powered flight, radio communication can be interrupted by plasma sheets around the vehicle or by the geometry of its trajectory. The data recorder captures everything for later analysis. At around T-minus 1 minute and 22 seconds, the Launch Control Center in Houston verify the first motion signal path, confirming that the liftoff detection system is live and ready. Around T-minus 56 seconds, swing arm 9, the crew access arm, swings to its standby position, poised to retract fully at T-minus 5 seconds. 30 to 40 seconds before launch, the commander performs the last active step by the crew before liftoff, the alignment of the backup attitude system. The inertial measuring unit is the gold standard for reference. The backup system uses coarse gyros mounted directly to the spacecraft structure. With one button press, the gyro display coupler synchronizes the backup system to the inertial platform. The spacecraft's navigation chain is now fully aligned for the violent minutes ahead. The crew has no more checklist items. Their work is done. They are strapped into couches surrounded by switches, lights, the faint hiss of oxygen flow, and the enormous quiet of a spacecraft moments away from leaving Earth. At around T-30 seconds, a preparation begins that few people ever discuss: the water deluge system arms. At liftoff, 340,000 gallons of water will flood the pad, starting at T plus 1.5 seconds, designed to protect the launch platform from 3,000-degree exhaust and the crushing acoustic force of 7.5 million pounds of thrust. At T-minus 22 seconds, the guidance reference release alert sounds. At T-minus 17 seconds, the stable platform inside the instrument unit is released. Its gyroscopes and accelerometers now free to track the vehicle's motion independently of the Earth. The launch vehicle digital computer starts time base 0. The PAO call echoes across the firing room. Guidance is internal. At around T-minus 16 seconds, swing arm 1 retracts. This arm carries the final ground support electrical and pneumatic connections to the command module. When it moves away, the rocket stands entirely alone, held to the pad by 4 massive hold-down arms, gripping the engine fairing structure of the first stage. 8.9 seconds before launch, the terminal countdown sequencer issues a command that begins one of the most violent mechanical processes ever engineered: the ignition of the F-1 engines. These engines are each fed by turbopumps that spin to 5,500 RPM in less than 4 seconds, slamming petroleum-based fuel and supercold oxidizer into the combustion chamber at mixture ratios and flow rates that push the limits of structural metallurgy. Ignition is guaranteed by a pyrotechnic start system using hypergolic fluid, triethyl aluminum, and triethylborane, chemicals that ignite on contact with oxygen. There is no second chance. An F-1 engine cannot be relit. The engines ignite in a staggered pattern to reduce side loads on the vehicle. When the center engine lights first, then, within 200 to 300 milliseconds, 2 outboard engines ignite, and finally, the last pair. As the first engine lights, the flame beneath the rocket is a churning cloud of carbon-rich exhaust. The Saturn V expels thousands of kilograms of gas per second, and the flame deflector channels the blast sideways into trenches designed specifically to dissipate the shock. At this same moment, another event occurs that is often overlooked but critical to flight: the retraction of the cue ball cover. The cue ball is a hemispherical air data sensor mounted on the tip of the launch escape tower, containing 8 pressure ports arranged around its nose. These ports measure the angle at which the rocket slices through the atmosphere, and they are life-critical. In a pad abort, the cue ball data tells the launch escape system which direction to steer the command module away from danger. For hours before launch, a foam cover protects it from debris and weather. At T-minus 8.9 seconds, a pneumatic system pressurized to 600 psi of gaseous nitrogen cuts the retaining cable. A mechanism on the mobile launcher pulls the cover halves upward and away, exposing the sensitive ports to the air they will soon measure. At 6.4 seconds before liftoff, all 5 F-1 engines are running. The rocket still stands pinned to the pad. The hold-down arms monitor thrust sensors, ensuring each engine has reached the required thrust level. If any single F-1 reads below 90% thrust, the sequencer commands an automatic cutoff, a safety system that was never triggered in 13 flights. Only when all 5 thrust readings exceed their launch criteria does the sequencer release the hold-down arms. They pivot away in unison. For a brief instant, even with full thrust, the rocket barely moves. It must overcome 6.2 million pounds of weight. But as the engines reach full steady thrust, the vehicle rises a tiny fraction, on the order of 1 to 2 inches, just enough to actuate release and liftoff sensing switches. This tiny movement triggers the instantaneous retraction of several swing arms that remain connected. Movies often dramatize these arms retracting one at a time. In reality, they snap back simultaneously in milliseconds, pulled clear before they can strike the vehicle. At about 0.6 of a second after the rocket begins climbing, on one of the most critical signals of the countdown occurs, the disconnect of the instrument unit umbilical. This umbilical carries data, power, and conditioning lines between the ground and the Saturn V's brain, the launch vehicle digital computer and its guidance platform. When the connection breaks, a circuit opens and the computer recognizes liftoff. This moment starts Timebase 1 inside the computer. Timebase 1 is the reference for every event during the first stage burn. Engine gimbaling schedules, pitch and roll programs, abort mode switching, and guidance reference comparisons. Without this precise start time, the guidance equations would drift and the vehicle could not follow its intended trajectory. The engineers who designed this system understood the danger of a false signal. Suppose wind, vibration, or an accidental mechanical strike disconnected the umbilical prematurely. The computer would then incorrectly assume liftoff. To prevent this, the launch vehicle digital computer cross-checks the accelerometers. Only if it sees at least 1 g of upward acceleration after guidance reference release does it accept umbilical disconnect as genuine. This layered logic means that only true physical ascent can trigger Timebase 1. But on every flight, including Apollo 11, the sequence was perfect. The Saturn V was climbing, the umbilical disconnected, and the launch vehicle digital computer began its ascent program without ambiguity. At T plus 1.35 seconds, something happens that many spectators once mistook for an anomaly. The Saturn V deliberately yaws 1.25 degrees away from the launch tower. This is the programmed yaw maneuver, a brief, our intentional sideways nudge to ensure the vehicle clears the tower structure with safe margin. It is one of the first commands of the guidance program, and it is over almost before it begins. Within the first second of powered flight, the computer transmits the liftoff discrete to the command module's computer. Inside the spacecraft, several indicators respond instantly. The liftoff light illuminates. The mission timer starts from 0. And the commander calls the words that have echoed across every crewed American launch since Mercury. The clock is running. At this moment, all human involvement in the launch is effectively complete. The Saturn V is in the hands of its guidance platform and digital computer. It is a fully autonomous 6.2 million pound spacecraft rising on a column of fire visible for dozens of miles. On the next stages of flight, the pitch program, the roll program, the reduction of loads as the vehicle breaks the sound barrier, the shutdown of engines, staging, and the ignition of the second stage all flow from this one moment. The last 3 minutes before Saturn V liftoff are no longer a countdown. They have become the opening chapter of a mission to the moon. This choreography succeeded 13 out of 13 times, proof of Apollo's engineering edge. If you enjoyed this dive into the final moments before Saturn V liftoff, a like or a share really helps more people discover these stories. And if you want to support the channel and get early access or members-only videos, you can join the channel anytime. Thanks for watching and for keeping Apollo history alive. When Apollo 11 left Earth orbit, its path to the moon was not determined by what the crew could see or by onboard guesswork. From the moment trans-lunar injection was complete, after the S-4B stage's final burn, the problem of knowing where the spacecraft was and where it would be days later shifted almost entirely to Earth. This journey was guided by an invisible global system. A network of antennas, clocks, radio links, and computation centers measure distance and velocity not in miles on a map, but in time delays, Doppler shifts, and continuously updated state vectors. The astronauts did not navigate by sight. They flew a trajectory that was calculated, verified, and refined on the ground by the manned spaceflight network and by flight dynamics teams inside Mission Control. In this video, we're going to look at how Apollo 11 was tracked across nearly 250,000 miles of space, how radio signals became distance, how frequency shifts became velocity, and how Earth-based prediction and measurement kept the mission inside margins measured in feet per second. Because in a very real sense, the path to the moon was never flown alone. It was computed, monitored, and validated continuously from the ground. Throughout trans-lunar and lunar orbit flight, the central requirement was not simply to know where Apollo 11 was, but to maintain a validated state vector, accurate enough that small deliberate velocity changes, on the order of tens of feet per second, could be planned, executed, and verified with tight margins. Tracking in this regime was neither visual nor intuitive, or else it was based on precise time-of-flight measurements, Doppler frequency shifts, and the known geometry of a global antenna network, all referenced to inertial frames and ephemerides rather than to any surface landmark. The Manned Spaceflight Network, or MSFN, was the backbone of Apollo 11's tracking and communications. It consisted of roughly 30 ground stations, 4 tracking ships, Vanguard, Mercury, Redstone, and Huntsville, plus aircraft, all distributed so that at least one high-gain antenna would see the spacecraft throughout its path to and from the moon, except during occultation behind the lunar body. These stations were managed from Goddard Space Flight Center, which oversaw network configuration, data routing, and the health of the ground segment, while Mission Control in Houston consumed the resulting data stream for trajectory and systems decisions. The network layout was not arbitrary. Stations were placed in North America, the Atlantic, Europe, Africa, the Indian Ocean region, Australia, and the Pacific to ensure coverage of key dynamic events, including trans-lunar injection, mid-course windows, lunar orbit insertion, and later trans-Earth injection and reentry. Unknown to most, Australian stations like Honeysuckle Creek and Tidbinbilla were critical for confirming the trans-lunar injection burn when American stations had lost line of sight. To fill unavoidable geographic gaps, the MSFN deployed tracking ships and aircraft, extending line of sight beyond continental coastlines. Ships bobbing in Pacific storms to track burns that no land station could reach, so that no single hemisphere could lose the spacecraft during critical maneuvers. Goddard didn't just route data remotely. It deployed flight controllers directly to key stations, creating semi-autonomous outposts capable of real-time decisions, even when communication delays to Houston made waiting impractical. Houston had no antennas. Every measurement of Apollo 11's position and velocity originated at the geographically distributed MSFN sites. Apollo 11 relied on the unified S-band system for long-range communications. A single S-band link carried ranging codes, Doppler coherent carrier, telemetry, and voice between the spacecraft and the MSFN dishes. See, once the spacecraft was about 30,000 miles from Earth, the earlier VHF systems used near Earth became secondary. From that point onward, the USB transponder and the large MSFN antennas were the sole means for maintaining precise tracking and full-fidelity telemetry. The S-band transponder implemented coherent turnaround. It received an uplink at a well-defined frequency and retransmitted a downlink whose frequency was an exact fixed ratio, 240/221, of the uplink, preserving Doppler information in the process. This design ensured that any observed frequency shift at the ground antenna could be unambiguously attributed to the spacecraft's relative motion along the line of sight, rather than to uncontrolled offsets in the onboard oscillator. A two-way ranging used pseudo-random noise codes, transmitted at 994 kilobits per second from the ground, received and coherently retransmitted by the spacecraft, and correlated back at the ground station to determine the signal's round-trip delay with high precision. The ranging codes were structured into subcodes, designated A, B, C, and X, whose correlation properties allowed the ground equipment to resolve ambiguities over the enormous distances involved and to derive an unambiguous range all the way to lunar distance. In operational terms, the ground system compared the transmitted PRN code to the returned code, adjusted an offset until correlation peaked, and translated that offset into a propagation time and thus a slant range. For Apollo-class distances, range resolution was on the order of 1 to 1.5 meters, with the limiting factor being not code quantization but the accuracy and stability of the timing reference and the integration period over which correlation was measured. Complementing range, the same coherent S-band link supported two-way Doppler measurements. The carrier frequency shift between transmitted and received signals was integrated to yield line-of-sight velocity, with resolution on the order of 0.1 to 0.5 feet per second, and accumulated distance change. Because the downlink frequency was locked to the uplink by the known 240/221 ratio, any deviation from the expected downlink frequency at the ground antenna corresponded directly to radial motion. Once Earth's rotation and planetary dynamics were removed, ground receivers used highly stable oscillators and frequency synthesizers, stepping in increments as small as 1 Hz, to track the evolving Doppler shift as the spacecraft receded from Earth or approached the Moon at thousands of feet per second. By integrating Doppler over time, the tracking system could refine range estimates between discrete PRN range measurements, effectively interpolating the spacecraft's path and maintaining a continuously updated state even when active ranging was not being exercised. All of this depended on time. The MSFN relied on precise frequency standards and time dissemination across the entire network so that the ranging codes and Doppler integration were referenced to stable, known clocks. Any timing error in the measurement chain translated directly into distance uncertainty. A microsecond of error in round-trip time corresponded to roughly 500 feet of apparent range error, making nanosecond-level stability essential for meter-class resolution. To control this, ground stations used disciplined oscillators and synchronization procedures maintained by Goddard and supporting timing facilities, ensuring that each station's time base contributed repeatable, calibratable errors rather than unbounded drift over the multi-day trans-lunar coast. The cumulative effect of clock stability, code design, and Doppler integration allowed the network to maintain Apollo 11's state vector within tight dispersions, sufficient to plan mid-course corrections in single-digit feet-per-second increments. In parallel with tracking data, the same S-band link carried engineering telemetry, pressures, temperatures, voltages, system states, and guidance computer data, all multiplexed and encoded for transmission to the MSFN stations. When at each station, telemetry receivers demodulated the downlink, separated the telemetry stream, and sent it over the NASCOM network to Houston, where dedicated backroom teams in console positions monitored parameters on strip charts and displays. The monitoring philosophy was explicitly trend-oriented rather than alarm-driven. Controllers watched slow drifts, correlations between subsystems, and the behavior of critical quantities across major maneuvers, comparing them against pre-computed envelopes from analysis and earlier missions. While limit alarms existed, they were not the primary decision tool. Instead, the integration of multi-parameter behavior over hours of flight was used to validate that the spacecraft and its guidance system were behaving consistently with the trajectory that the tracking data indicated. The individual MSFN stations produced raw measurements, range rate, and antenna pointing angles, along with quality indicators. These were routed via NASCOM through Goddard to Mission Control, where they entered the flight dynamics processing chain and were combined into a single best estimate state vector using weighted least squares and related estimation techniques. When more than one station had the spacecraft in view, their independent measurements were not simply averaged. Each station's data carried a known error model reflecting antenna geometry, local atmospheric conditions, and equipment calibration. and the estimation algorithms gave higher weight to data with better formal accuracy. Cross-checks between stations allowed outliers to be detected and either downweighted or excluded. Sign consistency over time served as an additional validation that no hidden bias was distorting the navigation solution. Mission Control in Houston did not operate as a tracking station. It had no large antennas and did not generate primary range or Doppler data. Its role was to receive already measured tracking and telemetry data, run it through trajectory determination and systems analysis tools, and then make integrated decisions about burns, attitude strategies, and go/no-go calls. Within Mission Control, flight dynamics officers and their support rooms focused on the state vector, ingesting MSFN measurements, updating the onboard guidance solution as needed, and comparing predicted trajectories with safety and mission requirements. Each state vector uplinks to the spacecraft's guidance computer occurred roughly 24 hours after trans-lunar injection, correcting discrepancies that had grown from small errors accumulated during Earth orbit. The key point is that Houston functioned as a computation and coordination node, while all direct sensing of Apollo 11's position and velocity occurred at the geographically distributed MSFN sites. Mid-course corrections were deliberate adjustments to the trans-lunar trajectory, planned in advance as opportunities, but only executed if tracking data and analysis showed that the actual path diverged from the desired corridor by more than tight tolerances. For Apollo 11, 4 mid-course correction windows were available during trans-lunar flight, but only one was required. A 3-second SPS burn executed roughly 24 hours after trans-lunar injection, adding 21 feet per second. The planning sequence started with MSFN range and Doppler data being accumulated over substantial arcs, then processed to refine the state vector and propagated forward to key mission events such as lunar orbit insertion and the targeted perihelion altitude. If the predicted conditions deviated beyond allowable margins, the flight dynamics team designed a small burn, specifying magnitude, direction in the appropriate reference frame, and timing. After execution, the same tracking chain, range, Doppler, and angle data from multiple stations was used to verify the achieved delta V and to confirm that the updated trajectory met requirements without needing further correction at the next window. Yet redundancy in tracking and data processing was fundamental. Where possible, multiple MSFN stations, and in some cases deep space network antennas and backup roles, observed the spacecraft simultaneously, providing overlapping measurements that could be cross-checked. The network also incorporated ships and aircraft to guard against coverage loss over oceans or in the event of local failures, making it unlikely that a single hardware issue would leave Apollo 11 untracked at a critical time. Validation extended beyond hardware redundancy. Separate processing chains and independent teams compared trajectory solutions, and predicted observables were contrasted with newly arriving measurements to detect subtle discrepancies. The philosophy assumed that any single data source or model could be wrong, and relied on agreement between multiple stations, multiple passes, and multiple analytical approaches before committing to major burns, such as mid-course corrections or lunar orbit insertion. As Apollo 11 moved away from Earth and approached the region where the gravitational influences of Earth and Moon were comparable, tracking strategies shifted from essentially Earth-centered geometry to a more complex two-body plus perturbations framework. The same MSFN measurements, range and Doppler, were still referenced to Earth-based antennas, but the trajectory models used in Mission Control's computations began to emphasize lunar ephemeris accuracy and the desired conditions at the lunar sphere of influence. This transition did not reduce the reliance on ground tracking. It changed the questions being asked of the data. Instead of primarily asking how closely the spacecraft followed a specific Earth departure corridor, the flight dynamics team focused on whether the trans-lunar path would intersect the planned lunar orbit insertion corridor at the required altitude, inclination, and timing. During lunar orbit insertion, MSFN tracking supported pre-burn targeting and post-burn assessment, but not the burn itself while the spacecraft was behind the moon. Before the maneuver, ground data and analysis were used to compute the required SPS burn, start time, duration, and orientation to place Apollo 11 into the planned lunar orbit. Once Apollo 11 disappeared behind the moon, line-of-sight radio contact was lost, and with it any possibility of real-time range or Doppler measurements. During this interval, a mission control relied entirely on prediction, propagating the pre-burn state vector forward with the planned burn parameters and a known lunar gravity model, then predicting the time at which the spacecraft would re-emerge and reacquire signal. When contact returned, the first few minutes of range and Doppler were critical, allowing rapid comparison between predicted and actual orbits and confirming that the insertion burn had produced the desired result. Throughout Apollo 11's trans-lunar and lunar orbit phases, tracking and navigation alternated between regimes dominated by fresh measurements and regimes dominated by prediction. During continuous visibility, MSFN measurements constrained the state vector tightly and provided immediate feedback after small burns. During line-of-sight gaps, the same state vector was propagated forward under known dynamics, with confidence bounds defined by previous tracking accuracy and model uncertainty. The distinction between measurement and prediction was carefully maintained. Measurements were treated as noisy observations of the spacecraft's true state. Predictions were outputs of models that assumed particular forces and executed burns. Navigation was the estimation process that reconciled the two, integrating range and Doppler with dynamical models to produce the best estimate state vector. Guidance was the use of that state vector to generate specific commands to the spacecraft's propulsion and attitude systems. From trans-lunar injection through lunar orbit insertion, Apollo 11's path was known not by sight, but by a global coordinated system of antennas, clocks, codes, and numerical methods, all operated by ground teams who never left Earth. The manned spaceflight network and its supporting infrastructure transformed S-band signals into continuous knowledge of position and velocity, while mission control integrated that knowledge into navigation solutions and operational decisions, ensuring that each planned burn placed the spacecraft exactly where later events required it to be. In this sense, the journey to the moon was anchored firmly on the ground. The astronauts executed maneuvers and monitored onboard guidance. But the underlying certainty that Apollo 11 would intersect a precise corridor at the moon, at the correct time and velocity, came from Earth-based tracking and prediction, maintained without interruption except during the predictable, modeled blackout behind the lunar body. If this kind of engineering-level breakdown is useful to you, consider giving the video a like. It helps more of the right people find this content. And if you'd like to support deeper dives into Apollo systems and operations, you can also join the channel. Thanks for watching. Resting in the Johnson Space Center parking area lies a colossal 363-foot Saturn V launch vehicle, the mightiest apparatus ever constructed by our species, collecting grime rather than venturing into deep space. Meet SA-515. A complete perimeter walk around its foundation requires a full 5 minutes to traverse just the initial segment. Crane your neck toward its summit and witness an object exceeding the height of 36 stacked floors. This behemoth was destined to transport Apollo 18 toward our lunar neighbor. Astronauts had been designated. The touchdown location had been determined. Scientific instruments were constructed and prepared for deployment. Launch day never arrived. Yet the explanation doesn't involve extraterrestrial beings or shadowy governmental plots. It represents something decidedly more earthbound and profoundly more heartbreaking. What follows explains how our species' most remarkable voyage beyond Earth, operating at the absolute zenith of its technical prowess, faced intentional destruction and abandonment. The reason wasn't inability to venture onward, but a conscious decision to halt progress. Conventional accounts describe mere financial restrictions, the unavoidable conclusion of an expensive undertaking. Yet classified documents expose something more sinister: the calculated termination of humanity's finest exploratory endeavor precisely when it achieved maximum scientific effectiveness. This recounts a phantom expedition and the price we paid by forsaking it. Transport yourself to 1970, positioned inside the vehicle assembly building at Kennedy Space Center. You're an engineering professional who dedicated the previous 10 years perfecting the most advanced exploratory apparatus ever conceived. Surrounding you, work crews assemble spacecraft representing the apex of accumulated knowledge. Each setback studied, each component enhanced, each insight from previous expeditions incorporated into the machinery. This represents Apollo's intended culmination. By 1970's arrival, NASA had evolved lunar expeditions from risky ventures into polished scientific endeavors. Initial Apollo flights emphasized mere survival. Reach the destination, display the banner, return breathing. Apollo 18 was conceived as something significantly grander: a J-class expedition representing lunar exploration technology's summit. Consider the distinction between a vacationer capturing snapshots at the Grand Canyon versus a scientist dedicating 7 days charting its most profound mysteries. Statistics reveal the transformation. Apollo 18 planned 3 to 4 days inhabiting the lunar terrain, not Apollo 11's short, cautious intervals, but sufficient duration to create an authentic research station. The team would execute 3 distinct EVAs, accumulating 22 to 24 exploration hours. They'd install the Apollo Lunar Surface Experiments Package, ALSEP, a complex instrument array engineered to reveal the moon's most guarded information regarding interior composition and atmospheric conditions. Tremor detectors for identifying moonquakes, thermal probes for gauging internal heat levels, field sensors for charting magnetic properties. These transcended mere tools. They embodied inquiries we posed to existence. Additionally, they'd operate the lunar rover, an electrically powered transport capable of venturing 12 kilometers from touchdown coordinates, converting the expedition's scope from a confined zone surrounding the lander into legitimate exploration. Picture the contrast between confinement to your yard versus possessing transportation enabling county-wide investigation. That represented the rover's significance for lunar research. Candidate locations being evaluated: Copernicus Crater, Schroeder's Valley, featuring its characteristic Cobra Head volcanic formation, or Gassendi Crater, represented scientifically valuable landscapes previous expeditions hadn't accessed. These weren't merely attractive destinations. Copernicus was a comparatively recent impact formation potentially exposing materials beneath the moon's exterior layer. Schroeder's Valley was an enormous channel possibly containing evidence of prehistoric volcanic processes. Gassendi occupied the Mare-Imbrium boundary, where highland and mare formations intersected. Each location was a repository of lunar chronicles awaiting examination. The Saturn V vehicle, assigned to this expedition, SA-515, embodied engineering excellence's pinnacle. Position yourself beside one of its 5 F1 power plants, and you're observing a flared exhaust cone 12 feet in diameter, a mechanical blossom capable of generating 1.5 million pounds of force. Combined, all 5 engines could deliver 7.65 million pounds of thrust. Adequate power to propel 310,000 pounds completely to the moon. That equals 40 elephants' mass accelerated to 25,000 miles per hour, then projected across 250,000 miles of emptiness. What amplifies this achievement's magnitude? Launching a Saturn V demanded identical massive resources and national organization as conducting a Super Bowl. Thousands of staff functioning in flawless coordination. Months of preparation for one occurrence. Complete exactness, mandatory at every tier. The distinction? One occasion would captivate the planet for an afternoon. The alternative would enhance human understanding for successive generations. Yet there's something requiring comprehension about reaching this achievement. At Grumman and North American Rockwell facilities, engineers had recently commemorated finishing Lunar Module 13 and Command and Service Module 115, the final specimens of their category. These weren't experimental prototypes accumulating grime in storage facilities. They were flight-certified vehicles fueled by dedication and skill of thousands of laborers who trusted their workmanship would attain the moon. Every connection was flawless. Every pathway was verified. Every mechanism had been enhanced through insights gained from preceding expeditions. NASA had ultimately resolved the initial difficulties. The expeditions were more secure than previously. The research was more advanced than anyone had envisioned feasible back in 1961 when Kennedy delivered his commitment. Apollo 18 embodied the instance when we'd evolved from frantic trailblazers into assured explorers, when the moon was no longer a target, but a research facility. This was humanity at its peak, constructing apparatus that challenged physics, posing inquiries that extended beyond ourselves, advancing forward not because it was simple, but because it was challenging. Yet while engineers refined their apparatus, a separate countdown had commenced, one destined to demolish the program internally. The year was 1970, and America was hemorrhaging funds. Vietnam was devouring $2 billion monthly, not annually, monthly. That's $67 million daily, disappearing into Southeast Asian jungles. Urban centers were erupting. The civil rights movement had revealed profound injuries in American civilization, demanding immediate focus and resources. And NASA was requesting Congress to authorize 3 additional moon expeditions, each requiring between $350 and $450 million in 1972 to gather additional specimens. Calculate the figures. One Apollo expedition required what you could utilize to construct educational facilities, medical centers, residential developments. That $400 million could sponsor initiatives directly impacting millions of Americans' existence. Meanwhile, evening broadcasts displayed casualty containers returning from Vietnam and demonstrations crowding thoroughfares. NASA discovered itself in an unwinnable situation, justifying the indefensible extravagance of lunar exploration while the nation was fragmenting at the foundations. Yet the actual destroyer wasn't solely the expense. It was the indifference. Following Apollo 11's space race victory, something terrible occurred to public engagement. The enchantment vanished. Television networks ceased transmitting live moonwalks. When Apollo 13 nearly concluded in catastrophe, the planet focused because mortality was compelling. Yet when Apollo 14 touched down successfully, indifference already experienced that. The most exceptional accomplishment in human chronicle had transformed into routine within 2 years' time. Consider that. We had converted walking on another celestial body, something that had been imagination for humanity's entire existence until 1969, into background information by 1971. The already experienced that mindset established itself with stunning velocity. Inside NASA, the atmosphere was deteriorating. Internal communications between administration leadership and the White House conveyed increasing concern over escalating expenses and evaporating political backing. More disturbing were the scientific disputes developing within NASA itself. Certain researchers were quietly challenging whether supplementary expeditions would produce findings proportional to their astronomical cost. The principle of decreasing benefits was manifesting. Each fresh specimen collection from progressively distant lunar locations promised progressively smaller scientific advances. For the astronauts, this wasn't theoretical policy discussion. This was their existence. Vance Brand, Don Lind, and Harrison Schmitt were among the astronauts most regularly connected with Apollo 18 in NASA's provisional crew designations. These were individuals who had prepared for years, relinquished family time, devoted their existence to this instance. They'd mastered geology until they could recognize rock categories instantly. They'd rehearsed lunar touchdowns in simulators until the sequences were instinctive memory. They'd operated rovers across replicated moonscapes in Earth's most barren territories. Their expedition insignias were created. Their touchdown location was determined. And then, one September 1970 day, they received notification. Your expedition no longer exists. Don Lind's experience exemplifies the personal devastation. He earned recognition as the most unfortunate astronaut in NASA chronicles. Designated for Apollo 18, he observed his moon expedition dissolve. Years of preparation, thousands of simulator hours, geological expeditions across Earth's most lunar-resembling landscapes, all for a voyage that would never initiate. He was continuously reassigned as program emphasis shifted like sand underneath his position. Precisely as Apollo 18 ultimately represented his opportunity to traverse the moon, the expedition was terminated completely. The verdict arrived rapidly and harshly. In September 1970, NASA didn't merely terminate Apollo 18. They canceled Apollo 19 and 20 simultaneously, eliminating 3 expeditions in one action. The declaration was presented as financial prudence, but it was political preservation. Politicians had identified a convenient target for spending reductions, and Apollo's declining returns on public excitement made it susceptible. What rendered the cancellation especially merciless? The equipment was already constructed. The spacecraft existed. The astronauts had prepared for years. Engineers at Grumman and North American Rockwell had commemorated completing the final lunar module and command module for Apollo 18, unaware their labor would never fly. Yet the authentic tragedy wasn't merely the terminated expeditions. It was the intentional dismantling of capability. NASA didn't merely postpone Apollo 18. They demolished the infrastructure. The manufacturing facilities that constructed Saturn V vehicles were terminated and dismantled. The teams that had perfected lunar operations were dissolved. The organizational knowledge, the 1,000 minor insights gained from each expedition, was dispersed as engineers transferred to alternative projects or departed aerospace completely. The Saturn V SA-515, the vehicle that should have transported Apollo 18 to the moon, became a museum display. This wasn't a temporary obstacle. This was NASA rendering returning to the moon impossibly expensive for successive generations. By demolishing the capability to construct Saturn V vehicles, by dissolving the teams that understood how to operate them, by allowing the supply networks and specialized installations to vanish, they guaranteed that any future lunar program would require starting from nothing. The expense projections for Apollo 18 ranged from $350 to $450 million in 1972, a figure politicians contended could sponsor educational facilities, medical centers, and social initiatives during domestic crisis. They weren't mistaken about the nation's requirements, but they were making a selection about what species we wanted to become. Don Lind wouldn't journey to space until 1985 on a shuttle expedition that couldn't compare to the lunar voyage he'd forfeited. 15 years of anticipation. 15 years of observing that Saturn V SA-515 positioned in its museum presentation like a funeral memorial to what might have existed. And so, the vehicle that should have transported humanity further into the cosmos became a memorial to what we relinquished. We commenced with the official narrative that Apollo 18 was simply a casualty of spending reductions and declining interest. A footnote in Chronicles, a terminated expedition that nobody recalls. Yet the classified documents expose the deeper reality. It was a conscious selection, an instance when America determined that political convenience mattered more than cosmic ambition. The cancellation of Apollo 18 wasn't merely about one expedition. It represented the facility with which humanity can forsake its finest accomplishments. We had attained the moon. We had perfected the technology. We positioned ourselves at the summit of our capability, prepared to convert lunar exploration from short visits into sustained scientific discovery. And we departed. What conspiracy advocates understood correctly? There was a concealment. Yet it wasn't regarding aliens or covert expeditions. The actual concealment was hiding in plain observation, buried in congressional testimony and spending reports that nobody desired to examine. The mundane documents that exposed how we select what matters, what we're prepared to finance, and what we're prepared to forsake when the invoice arrives. Currently, that Saturn V SA-515 resides at the Johnson Space Center, positioned horizontally in a climate-regulated structure. It's a 363-foot memorial to unrealized potential. A vehicle that could have transported us to the moon, now a museum display that reminds us what occurs when we select the immediate over the eternal. You can traverse its length, place your palm along its exterior, and sense the significance of what we relinquished. Every hardware piece is documented in the historical archive. No covert launches, No apps and equipment, just meticulous documentation of what was constructed, what flew, and what concluded in museums. The astronauts supposedly lost on a classified lunar expedition. Vance Brand proceeded to fly on Apollo-Soyuz and recorded 3 additional expeditions aboard the space shuttle. Don Lind ultimately reached space in 1985, becoming a payload specialist and researcher. Harrison Schmitt flew on Apollo-17 instead, the final human to leave impressions in lunar powder. They weren't silenced. They weren't vanished. They were reassigned. Their careers continuing in complete view of the public archive. The conspiracy wasn't a covert moon installation or hostile extraterrestrials. It was the mundane apparatus of government selecting between competing emphases, between lunar exploration and social initiatives, between tomorrow's aspirations and today's emergency. This narrative matters currently more than previously. Apollo 18's cancellation remains a case examination in balancing ambition with sustainability, directly influencing NASA's cautious methodology to Artemis and contemporary lunar programs. Current expedition planners emphasize international cooperation, commercial partnerships, and modular exploration frameworks. Insights gained from observing Apollo's summit capability relinquished on the altar of short-term reasoning. The inquiry confronting us isn't whether aliens are authentic. It's whether we'll make the identical selections our predecessors made in 1970. Whether we'll once more exchange the stars for immediate political convenience. Because the actual secret of Apollo 18 wasn't concealed in classified documents or buried on the lunar terrain. It was written in spending memoranda and political addresses. The mundane documents that eliminated humanity's finest adventure. We didn't forsake the moon because of what we discovered there. We forsook it because we ceased looking upward. Apollo 18 never flew. Yet its phantom haunts every determination we make about space exploration currently. Because the actual inquiry wasn't whether we could continue proceeding to the moon. It's whether we possess the courage to complete what we initiated or if we'll continue constructing vehicles that never depart the surface. The selection, as always, is ours. If you appreciated this narrative, press subscribe for additional narratives where chronicles, technology, and human ambition intersect. Thanks for watching. On July 17, 1975, 2 spacecraft docked 140 miles above the Earth. An American Apollo Command Module and a Soviet Soyuz capsule locked together through a specially designed docking adapter. Astronauts and cosmonauts shook hands. They exchanged gifts. They shared meals. The world watched as the 2 superpowers, locked in a decades-long struggle for supremacy in space, appeared to declare peace. The mission was called Détente in Orbit, the handshake in space, a symbolic end to the space race that had consumed billions of dollars and dominated the imagination of 2 generations. President Ford called it a new era of cooperation. Soviet Premier Brezhnev echoed the sentiment. The press ate it up. But symbols are useful precisely because they obscure complexity. And the reality of Apollo-Soyuz was far more complex, far more calculated, and almost certainly more valuable to both nations' technical and intelligence communities than any public relations victory could ever be. This is the shadow history of Apollo-Soyuz. Not a rejection of the cooperation narrative, but a deeper look at what else was happening. A story of how unprecedented access created unprecedented opportunity. If you're interested in the real story behind space programs, the technology that actually flew, the decisions that never made the press releases, and how space became a strategic domain, subscribe to Space Cluster, like, and turn on notification. We focus on what was built, why it mattered, and where it really led. Now, back to the story. To understand what else was happening in July 1975, we need to go back to 1972. The space race was effectively over. America had won. 6 lunar landings, 12 men on the moon. The Soviets had failed to launch their N-1 lunar rocket successfully even once. Their moon program was dead, though they would not publicly admit it for another 2 decades. But the Soviet space program was far from finished. While America celebrated Apollo and prepared to wind down its manned spaceflight capability, the Soviets were building something different. They were building Salyut, a series of space stations designed for long-duration missions. They were perfecting automated docking systems. They were developing life support technology that could keep cosmonauts alive for months, not days. And American engineers and analysts were eager to understand how it all worked. The problem was access. You cannot inspect what you cannot reach. Soviet spacecraft were launched from Baikonur, deep in Kazakhstan. They were recovered in remote areas of the USSR. Western observers could watch launches from a distance. They could track orbital mechanics. They could intercept radio communications, but they could not touch the hardware. They could not examine the systems. They could not study the technology up close. Until Apollo-Soyuz. The official proposal came in 1972 during a meeting between NASA Administrator James Fletcher and Soviet Academy of Sciences President Mstislav Keldysh. The idea was simple: conduct a joint mission that would test compatible docking systems. This would allow future rescue missions if an American or Soviet crew were stranded in orbit. It was framed as a safety measure, a humanitarian gesture. Both sides understood it offered more than that. The Soviets saw an opportunity to demonstrate their continued relevance in space after the Apollo victories. They saw a propaganda win. They saw legitimacy. The Americans saw an opportunity to work closely with Soviet engineers and, for the first time, get inside a Soviet spacecraft. The centerpiece of the mission was the Androgynous Peripheral Attach System, or APAS. This was the docking mechanism that would connect Apollo and Soyuz. The term androgynous is critical. Previous docking systems used a probe and drogue design, where one spacecraft had an active probe that inserted into a passive drogue on the other spacecraft. This required one spacecraft to be designated active and one passive. APS eliminated that distinction. Either spacecraft could dock with either spacecraft. The mechanism consisted of 3 pedals on each docking ring that would guide and capture the opposing spacecraft, then retract to form a pressurized tunnel. It was elegant. It was sophisticated. The APAS 75 system was formally co-developed by American and Soviet engineers through a joint design process, though it built heavily on Soviet concepts originally developed for their lunar program and Salyut stations. American engineers contributed significantly to the final design. But more importantly, the collaboration gave American engineers their first opportunity to study, in exhaustive detail, how Soviet docking technology actually worked. The implications of this were significant. Docking technology is fundamental to space operations. It determines how you assemble structures in orbit. It determines how you resupply stations. It determines how you conduct rendezvous operations. The APAS collaboration revealed Soviet approaches to guidance, to structural engineering, to materials science, to redundancy and fail-safe mechanisms. Every specification, every tolerance, every design choice was a window into Soviet engineering philosophy and capability. But APAS was just the beginning. The real technical windfall came from the mission itself. The Apollo crew for this mission was carefully selected. Commander Thomas Stafford had flown Gemini 6, Gemini 9, and Apollo 10. He was an experienced test pilot and a general in the Air Force. Docking module pilot Deke Slayton was one of the original Mercury 7, grounded for years due to a heart condition but finally cleared to fly. Command module pilot Vance Brand was a test pilot and aerospace engineer. These were experienced professionals. They were trained observers, and it would be naive to think they did not receive briefings on what to look for. The Soviet crew was equally carefully selected. Commander Alexei Leonov was a hero, the first man to walk in space. Flight engineer Valery Kubasov was an experienced engineer who had flown on Soyuz 6. They were chosen to present the best face of the Soviet program. They were chosen to impress. And impress they did. But while they focused on demonstrating Soviet capabilities, the American crew was absorbing every detail. When the two spacecraft docked on July 17th, the Apollo crew entered the Soyuz capsule. They spent hours inside. They examined the control panels. They observed the life support systems. They noted the layout, the materials, the construction techniques. They took photographs, hundreds of photographs, official photographs for the press, yes, but also detailed technical photographs that would later be studied by engineers back home. The Soyuz spacecraft was a revelation. It was smaller than Apollo, more cramped, but in many ways more refined for its intended purpose. The Soviets had been flying Soyuz variants since 1967. They had refined the design through multiple iterations. Their environmental control system reflected years of experience with long-duration spaceflight, incorporating approaches to carbon dioxide removal that American engineers were keen to understand. The orbital module, the spherical section where the crews met and shared meals, revealed Soviet approaches to long-duration spaceflight. The equipment placement, the storage solutions, the attention to crew comfort for extended missions. All of this was valuable information for American planners thinking about Skylab follow-ons and future space station designs. But perhaps the most valuable insights came from simply watching the Soyuz systems operate. The Soviets were proud to demonstrate their spacecraft. They showed how the attitude control system worked. They explained their approach to orbital maneuvering. They demonstrated their communication systems. Every demonstration was an opportunity to learn. The American crew was not alone in this effort. On the ground, engineers and analysts were monitoring every transmission, every data point, every observation. The mission generated extensive technical reports. Some of these reports were classified. Some likely remain classified today. One particular area of focus was the Soyuz propulsion system. The spacecraft used a unified propulsion system where the same engines and fuel supply were used for both orbital maneuvering and the deorbit burn. This was different from the Apollo approach, which used separate systems. The Soviet design was more efficient in terms of mass, but potentially less redundant. Understanding these trade-offs was valuable for future American spacecraft design. Another area of interest was the Soyuz descent module. This was the section that would return the cosmonauts to Earth. Unlike Apollo, which used a pure ballistic reentry, Soyuz used a lifting reentry that allowed some control over the landing point. The heat shield design, the parachute system, the landing rockets that fired just before touchdown, all of this was observed carefully. The Americans did not get to physically examine the descent module during the mission, of course, but they observed it extensively during approach and docking. They photographed it from every angle. They noted the thermal protection system, the antenna placements, the thruster locations. Combined with signals intelligence and telemetry data collected during previous Soyuz flights, this visual inspection helped fill in gaps in American understanding. There was also a human element. The crews spent nearly 2 days together. They talked. They shared experiences. And while the conversations were monitored to some degree, people reveal things in casual conversation. The Soviet crew talked about their training. They talked about their facilities. They talked about future missions. Leonov, in particular, was talkative. He was a natural storyteller, and he enjoyed sharing his experiences. He talked about his spacewalk on Voskhod 2, about the near disaster when his suit inflated and he barely made it back into the airlock. He talked about the Soviet space program's history. The American crew listened, asked questions, and remembered. But intelligence collection is a two-way street. The Soviets were not naive. They understood that Apollo-Soyuz was a technical opportunity for them as well. They observed the Apollo spacecraft. They studied the American systems. They took their own photographs and notes. Both sides were learning from each other. Both sides were gaining insights they could not have obtained any other way. This was, in a sense, the unstated bargain of the mission. There are darker implications that some analysts have explored. Understanding how to dock with a spacecraft could theoretically inform how to approach a spacecraft that does not want to be approached. Understanding life support systems could theoretically inform how to disrupt them. Understanding propulsion systems could theoretically inform how to disable them. In 1975, the militarization of space was still largely theoretical. There were reconnaissance satellites, yes. There were early warning satellites. But the idea of actual combat in space, of spacecraft attacking other spacecraft, was still mostly confined to science fiction and classified Pentagon studies. Those studies existed, and the technical knowledge gained during Apollo-Soyuz likely fed into them in some capacity. The United States military was interested in understanding the capabilities and potential vulnerabilities of Soviet spacecraft. That much is reasonable to assume, even if the specific intelligence requirements and analysis remain classified. The APAS docking system was particularly relevant to future space operations. Understanding docking mechanisms has obvious implications for both cooperative and non-cooperative rendezvous scenarios. This is the shadow that some historians see hanging over Apollo-Soyuz. It was sold as cooperation, as détente, as the end of competition. But it may also have been preparation for a different kind of competition. A competition that could be fought not on the Moon, but in Earth orbit. The mission itself was a success by any measure. The docking worked perfectly. The crews got along well. The public relations value was enormous. Both sides declared victory. Both sides celebrated. But in the technical debriefs, in the engineering assessments, in the reports that were written and filed away, a different kind of story was being documented. A story of what had been learned. A story of what could now be understood. The irony is that the Soviets probably understood all of this. They were not fools. They knew the Americans were collecting technical intelligence. They knew the mission had multiple purposes. But they calculated that the propaganda value and the legitimacy of being treated as equals by the Americans was worth the exchange. They calculated that they were learning valuable things as well. And they calculated that détente, even pragmatic détente, was better than continued confrontation. They may have been right about that last point. Apollo-Soyuz did contribute to a thawing of Cold War tensions, at least temporarily. It did establish communication channels between the space programs that would prove valuable later. It did create personal relationships between engineers and astronauts that transcended politics. But it also demonstrated how cooperation could serve multiple purposes simultaneously. How openness could benefit everyone involved, including in ways that were never publicly discussed. The APS docking system itself had a long afterlife. It was used on the Soviet Mir space station. It was adapted for the Shuttle Mir program in the 1990s. It forms the basis for the docking systems used on the International Space Station today. Every time a spacecraft docks with ISS, it is using technology that descends directly from Apollo-Soyuz. And every time that happens, it is worth remembering that this technology was born from a mission that was simultaneously a symbol of peace and an unprecedented technical exchange. It was born from the understanding that in the Cold War, nothing was ever simple. Nothing was ever just what it appeared to be. The astronauts and cosmonauts who flew Apollo-Soyuz were, by all accounts, sincere in their desire for cooperation. Stafford and Leonov became genuine friends. They visited each other for decades after the mission. They advocated for continued cooperation. Their friendship was real, but they were also professionals serving their respective nations. They understood their roles. They understood that the mission had dimensions beyond what was publicly stated. They carried out those responsibilities while also building genuine human connections. That is the complexity of Cold War space exploration. That is the shadow history. Today, we celebrate Apollo-Soyuz as a milestone of cooperation. We point to it as proof that even in the darkest days of the Cold War, rivals could work together. We use it as a model for international space partnerships. And all of that is true, but it is not the complete picture. The complete picture is that Apollo-Soyuz was also an intelligence opportunity for both sides. It was also a chance to understand, in intimate detail, the capabilities of a rival spacecraft. The handshake in space was real. The technical exchange was real. Both things are true. Both things happened. And understanding that complexity is essential to understanding the real history of the space race and what came after. The lesson, if there is one, is not that cooperation was a lie. The cooperation was genuine. The lesson is that cooperation and competition coexisted, that diplomacy and intelligence collection coexisted, that personal friendship and national interest coexisted. That is the shadow history. And that is what we should remember as we plan future international space missions, future partnerships, future handshakes in space. They will be real. They will also be more than they appear. Both things will be true. And that does not diminish their value. It simply makes them more human. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.
In a museum parking lot at the Johnson Space Center sits a 363-foot Saturn V rocket, the most powerful machine humanity has ever built, gathering dust instead of exploring the cosmos. This is SA-515. Walk around its base and you'll need 5 minutes just to circle the first stage. Look up at its peak and you're staring at something taller than a 30-story building. This rocket was supposed to carry Apollo-18 to the moon. The crew was selected. The landing site was chosen. The experiments were built and ready to deploy. It never launched. But the reason why isn't aliens or government conspiracies. It's something far more human and far more tragic. This is the story of how humanity's greatest exploration program, at the absolute peak of its scientific capability, was deliberately dismantled and sacrificed. Not because we couldn't reach further, but because we chose not to. History tells you it was just budget cuts, the inevitable end of an expensive program. But the hidden files reveal something darker: the deliberate sacrifice of humanity's greatest exploration effort at the exact moment it reached its scientific peak. This is the story of a ghost mission, and what we lost when we abandoned it. Picture yourself in 1970, standing in the Vehicle Assembly Building at Kennedy Space Center. You're an engineer who has spent the last decade perfecting the most sophisticated exploration system ever built. Around you, teams are assembling spacecraft that represent the culmination of everything you've learned. Every failure analyzed, every system refined, every lesson from earlier missions baked into the hardware. This is the moment Apollo was built for. By 1970, NASA had transformed lunar missions from desperate gambles into refined scientific expeditions. The early Apollo missions were about survival. Get there, plant the flag, come home alive. But Apollo-18 was designed as something far more ambitious. A J-class mission, the pinnacle of lunar exploration technology. Think of it as the difference between a tourist snapping photos at the Grand Canyon and a geologist spending a week mapping its deepest secrets. The numbers tell the story. Apollo-18 would spend 3 to 4 days on the lunar surface, not the brief tentative hours of Apollo-11, but enough time to establish a genuine scientific outpost. The crew would conduct 3 separate EVAs, totaling 22 to 24 hours of exploration time. They'd deploy the Apollo Lunar Surface Experiments Package, ALSEP, a sophisticated array of instruments designed to unlock the moon's deepest secrets about its interior structure and environment. Seismometers to detect moonquakes, heat flow experiments to measure the moon's internal temperature, magnetometers to map its magnetic field. These weren't just instruments, they were questions we were asking the universe. And they'd have the lunar rover, an electric car that could travel up to 12 kilometers from the landing site, transforming the mission's reach from a small circle around the lander into genuine exploration. Imagine the difference between being stuck in your backyard versus having a car that lets you explore your entire county. That's what the rover meant for lunar science. The target sites under consideration: Copernicus Crater, Schroeder's Valley with its distinctive Cobra Head volcanic region, or Gassendi Crater, represented scientifically rich terrain that previous missions hadn't reached. These weren't just pretty locations. Copernicus was a relatively young impact crater that could reveal what lay beneath the moon's surface crust. Schroeder's Valley was a massive channel that might hold secrets about ancient volcanic activity. Gassendi sat at the edge of Mare Imbrium, where highland and mare geology collided. Each site was a library of lunar history waiting to be read. The Saturn V rocket designated for this mission, SA-515, represented the culmination of engineering perfection. Stand next to one of its 5 F1 engines, and you're looking at a bell-shaped nozzle 12 feet across, a mechanical flower that could generate 1.5 million pounds of thrust. Together, all 5 engines could produce 7.65 million pounds of thrust, enough force to lift 310,000 pounds all the way to the moon. That's the weight of 40 elephants, accelerated to 25,000 miles per hour, then hurled across 250,000 miles of void. Here's what makes this even more staggering. Launching a Saturn V required the same immense resources and national coordination as hosting a Super Bowl. Thousands of personnel working in perfect synchronization, months of planning for a single event, total precision required at every level. The difference? One event would thrill the world for an afternoon. The other would advance human knowledge for generations. But there's something you need to understand about what it took to reach this point. At Grumman and North American Rockwell, engineers had just celebrated completing Lunar Module 13 and Command and Service, Module 115, the last of their kind. These weren't prototypes gathering dust in warehouses. They were flight-ready vehicles, fueled by the pride and expertise of thousands of workers who believed their craftsmanship would reach the moon. Every weld was perfect. Every circuit was tested. Every system had been refined through lessons learned from earlier missions. NASA had finally solved the early problems. The missions were safer than they'd ever been. The science was more sophisticated than anyone had dreamed possible back in 1961, when Kennedy made his promise. Apollo 18 represented the moment when we'd transformed from desperate pioneers into confident explorers, when the moon was no longer a destination, but a laboratory. This was humanity at its finest, building machines that defied physics, asking questions that reached beyond ourselves, pushing forward not because it was easy, but because it was hard. But while engineers perfected their machines, a different kind of countdown had already begun, one that would destroy the program from within. The year was 1970, and America was bleeding money. Vietnam was consuming $2 billion per month, not per year, per month. That's $67 million every single day, vanishing into the jungles of Southeast Asia. Cities were burning. The civil rights movement had exposed deep wounds in American society that required urgent attention and resources. And NASA was asking Congress to fund 3 more moon missions, each costing between $350 and $450 million in 1972 dollars, to collect more rocks. Do the math. A single Apollo mission cost what you could use to build schools, hospitals, housing projects. That $400 million could fund programs that would directly touch the lives of millions of Americans. Meanwhile, the nightly news showed body bags coming home from Vietnam and protests filling the streets. NASA found itself in an impossible position, defending the indefensible luxury of lunar exploration while the nation was coming apart at the seams. But the real killer wasn't just the cost, it was the apathy. After Apollo 11 won the space race, something terrible happened to public interest. The magic faded. TV networks stopped broadcasting live moonwalks. When Apollo 13 nearly ended in disaster, the world tuned in because death was dramatic. But when Apollo 14 landed safely, yawn. Been there, done that. The most extraordinary achievement in human history had become routine in less than 2 years. Think about that. We had transformed walking on another world, something that had been fantasy for all of human history until 1969. into background noise by 1971. The been there, done that mentality took hold with breathtaking speed. Inside NASA, the mood was darkening. Internal memos between agency management and the White House expressed growing alarm over escalating costs and vanishing political support. More troubling were the scientific debates brewing within NASA itself. Some researchers were quietly questioning whether additional missions would yield discoveries proportional to their staggering expense. The law of diminishing returns was setting in. Each new rock collection from increasingly remote lunar sites promised incrementally smaller scientific breakthroughs. For the astronauts, this wasn't abstract policy debate. This was their lives. Vance Brand, Don Lind, and Harrison Schmitt were among the astronauts most frequently associated with Apollo 18 in NASA's tentative crew assignments. These were men who had trained for years, sacrificed time with families, dedicated their lives to this moment. They'd studied geology until they could identify rock types at a glance. They'd practiced lunar landings in simulators until the procedures were muscle memory. They'd driven rovers across simulated moonscapes in Earth's most desolate regions. Their mission patches were designed. Their landing site was chosen. And then, one day in September 1970, they were told, "Your mission no longer exists." Don Lind's story epitomizes the personal devastation. He became known as the unluckiest astronaut in NASA history. Selected for Apollo 18, he watched his moon mission evaporate. Years of preparation, thousands of hours in simulators, geological expeditions across Earth's most lunar-like landscapes, all for a flight that would never launch. He was repeatedly reassigned as program priorities shifted like sand beneath his feet. Just as Apollo 18 finally represented his chance to walk on the moon, the mission was canceled entirely. The decision came swiftly and brutally. In September 1970, NASA didn't just cancel Apollo 18, they terminated Apollo 19 and 20 as well, killing 3 missions in a single stroke. The announcement was framed as fiscal responsibility, but it was political survival. Politicians had found an easy target for budget cuts, and Apollo's diminishing returns on public enthusiasm made it vulnerable. Here's what made the cancellation particularly cruel. The hardware was already built. The spacecraft existed. The astronauts had trained for years. Engineers at Grumman and North American Rockwell had celebrated completing the last lunar module and command module for Apollo 18, unaware their work would never fly. But the true tragedy wasn't just the canceled missions. It was the deliberate dismantling of capability. NASA didn't just postpone Apollo 18, they destroyed the infrastructure. The production lines that built Saturn V rockets were shut down and dismantled. The teams that had perfected lunar operations were disbanded. The institutional knowledge, the 1,000 small lessons learned from each mission, was scattered as engineers moved on to other projects or left aerospace entirely. The Saturn V SA-515, the rocket that should have carried Apollo 18 to the moon, became a museum piece. This wasn't a temporary setback. This was NASA making returning to the moon impossibly expensive for generations. By destroying the capability to build Saturn V rockets, by disbanding the teams that knew how to operate them, by letting the supply chains and specialized facilities disappear, they ensured that any future lunar program would have to start from scratch. The cost estimates for Apollo 18 ranged from $350 to $450 million in 1972 dollars, a sum that politicians argued could fund schools, hospitals, and social programs at a time of domestic crisis. They weren't wrong about the nation's needs, but they were making a choice about what kind of species we wanted to be. Don Lind wouldn't fly in space until 1985 on a shuttle mission that couldn't compare to the lunar journey he'd lost. 15 years of waiting. 15 years of watching that Saturn V, SA-515, sit in its museum display like a funeral monument to what could have been. And so the rocket that should have carried humanity further into the cosmos became a monument to what we gave up. We began with the official story. that Apollo 18 was simply a victim of budget cuts and waning interest. A footnote in history. A canceled mission that nobody remembers. But the hidden files reveal the deeper truth. It was a deliberate choice, a moment when America decided that political expediency mattered more than cosmic ambition. The cancellation of Apollo 18 wasn't just about one mission. It represented the ease with which humanity can abandon its greatest achievements. We had reached the moon. We had perfected the technology. We stood at the peak of our capability, ready to transform lunar exploration from brief visits into sustained scientific discovery. And we walked away. Here's what conspiracy theorists got right. There was a cover-up, but it wasn't about aliens or secret missions. The real cover-up was hiding in plain sight, buried in congressional testimony and budget reports that nobody wanted to read. The boring documents that revealed how we choose what matters, what we're willing to pay for, and what we're willing to abandon when the bill comes due. Today, that Saturn V SA-515 sits at the Johnson Space Center, lying horizontally in a climate-controlled building. It's a 363-foot monument to unrealized potential, a rocket that could have taken us to the moon, now a museum piece that reminds us what happens when we choose the immediate over the eternal. You can walk its length, run your hand along its skin, and feel the weight of what we sacrificed. Every piece of hardware is accounted for in the historical record. No secret launches, no missing equipment, just careful documentation of what was built, what flew, and what ended up in museums. The astronauts supposedly lost on a classified lunar mission. Vance Brand went on to fly on Apollo-Soyuz and logged 3 more missions aboard the space shuttle. Don Lind finally made it to space in 1985, becoming a payload specialist and scientist. Harrison Schmitt flew on Apollo-17 instead, the last human to leave footprints in lunar dust. They weren't silenced. They weren't disappeared. They were reassigned, their careers continuing in full view of the public record. The conspiracy wasn't a secret moon base or hostile extraterrestrials. It was the mundane machinery of government choosing between competing priorities, between lunar exploration and social programs, between tomorrow's dreams and today's crises. This story matters now more than ever. Apollo 18's cancellation remains a case study in balancing ambition with sustainability, directly shaping NASA's cautious approach to Artemis and modern lunar programs. Today's mission planners emphasize international cooperation, commercial partnerships, and modular exploration architectures. Lessons learned from watching Apollo's peak capability sacrificed on the altar of short-term thinking. The question facing us isn't whether aliens are real. It's whether we'll make the same choices our predecessors made in 1970, whether we'll once again trade the stars for immediate political expediency. Because the real secret of Apollo 18 wasn't hidden in classified files or buried on the lunar surface. It was written in budget memos and political speeches, the mundane documents that killed humanity's greatest adventure. We didn't abandon the moon because of what we found there. We abandoned it because we stopped looking up. Apollo 18 never flew, but its ghost haunts every decision we make about space exploration today. Because the real question wasn't whether we could keep going to the moon, it's whether we have the courage to finish what we started, or if we'll keep building rockets that never leave the ground. The choice, as always, is ours. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.